Good morning, everyone. I hope you guys had a very well-rested day one of Devcon. I'm sure that you guys all went to bed super early. Today we're going to have a few talks on core protocol stuff, and I want you to remember to take any conversations outside. The bathrooms are down and to the right. And there's going to be a QR code on the screen for anybody to ask any questions. And so if you have questions, you can submit them during the talk, and then after the talk, we'll go through the most upvoted questions. So first up, we have Han from Nethermind, who's going to talk to us about state expiry.
Right. Cool. So it's the first session, so I want to kick things off with a little bit of fun. I'm going to give away 0.01 ETH to whoever that remembers the first ever smart contract that they have deployed. You can raise up your hand if you still remember the address. Okay, I actually expected a few, but I didn't expect like none. But it's okay. Like I didn't remember the first ever smart contract that I deployed, and that's normal. When we enter the space, we probably think that smart contracts are cool. We play around with a template or two to deploy some like fake token or like NFT contracts and just send some test transactions. Yeah, and that's totally fine, but you just forget about it. But the thing is that the data is still there, right? But you, me, and the rest of the ecosystem will likely never use it again, so why store it on-chain? So today, what I'm going to talk about is really, I'm going to go through the problems that we have with state growth, the proposed solutions that we have with state expiry, and where we are headed next. So here's everything you need to know about state expiry. Let's get started. First, let's do a quick revisit on state. What does state mean on Ethereum is that state is represented by a Merkle-Patricia tree, MPT. So we call it the state tree. In the leaf nodes of the state tree, we have all the account objects. So each account will contain balance, nonce, root hash, and code hash. And if it's a contract account, then it would have its own storage tree as well. It's also an MPT, and in the leaf nodes of the MPT, of the storage tree, it will contain the 32 bytes slot values, right? So this is the overview of how state looks like on Ethereum. Let's zoom in a little bit by focusing on individual account object and slot keys. So given an account address, we can actually traverse from the root of the state tree down to the leaf node, and we will get the corresponding account object, right? Likewise, for slot key, we can traverse from the root node of the storage tree down to the leaf node, then we can get the corresponding slot value. So this is how we do the mapping. So really, if we really zoom in and just be abstract, right? Ethereum state is really consists of like a mappings of a series of mappings between addresses and account objects, and also slot keys to slot values. So these key value pairs, you can really think of it as the basic unit to measure state on Ethereum. When Ethereum started from Genesis, it started with a small set of key value pairs. As the chain progresses, as more blocks are included, you get more and more key value pairs. And the number just keep increasing, increasing, and increasing. It will never stop because state is unbounded. And this phenomena is called state growth, right? So this is the problem that we are trying to solve today. But why is this a problem? To quote Peter from Geth, Ethereum is slow because the state grows like crazy. What happens when the state size grows is that the number of nodes in the MPT grows, right? So in the client software implementation, that means that for every read-write event, what happens is it will require more database lookups. It will require more hash calculations. So all these are expensive operations. So when you have those scenarios, then your node will become slower. And it's just not just that, right? You also think about hardware storage. Every few years, you probably have to change your hardware to upgrade your SSD so that it can contain more state. So if you really think about it as a flow, when the state grows, what happens is that running a node costs more because you have to upgrade your hardware every few years, whether it's storage or like CPU or whatever. When you have that kind of scenario, that means that less people will be incentivized to run nodes, like normal people, like maybe just you and me. And when less people run nodes, then Ethereum become less decentralized, right? So that's like a effect of state growth. But I know what some of you may be thinking, right? Some of you may be thinking that it's fine, right? The innovation in hardware will probably outpace state growth. And that's true. But is it really as simple as changing hardware and your node will magically run again? It's not as simple as this. The reality is that you have to first go to a physical store or online store, purchase the hardware. You have to, once your hardware arrives, you have to reassemble your node, take out the screw, take out the cover, swap the hardware, put the hardware back, I don't know, like put the cover back, put the screw back. Then maybe you have to migrate your storage from the old disk to the new disk. During this process, if you messed up, if you made a mistake, what you need to do is that you need to wait hours to resync again from 0. And yeah, it's just a very terrible user experience. So no, it's not as simple as people may think. Yes, if you're technical, it's simple to you, but not for normal people, no. Running nodes should be easy, or at least we shouldn't make it harder than what it is right now. So looking back at the state, if you look at all the key value pairs, ask yourself this question. How many key value pairs were actually accessed recently, let's say in the past 1 year? Based on the analysis that I did, it was only about 20%. So really, what we are storing right now for the execution clients are 80% of the state that are unused in a long time. And what happens when we eliminate this 80% of the state? Wouldn't we get a slower state growth? Wouldn't we be able to reduce the hardware storage requirements? Wouldn't we be able to build better execution client, a more efficient one? So that is what we are trying to do with state expiry. The concept of state expiry is simple. It has one key objective, which is to expire now and revive later. We want to provide a way to expire the stale data on-chain while providing a way for users to revive those data. There are two key questions that we need to answer for this objective. First, how do we know if a state is expired? Second, how do we revive expired state? And let's think this through together. First, we can look at the current MPT, right? So this is the structure of the MPT. We are only going to focus on the values because those values are the ones that we want to expire. To answer the first question, how do we know if a state is expired? Well, you can take a few seconds to think about it. The most straightforward way is to add some sort of a metadata to measure the state or the values, right? So here, what I'm going to do here is to add something called an access period to it. So an access period, you can think of it as like measured in blocks, or basically like one period is equals to 6 months, maybe. So when you have a period that corresponds to each value, then we can already answer our first question. In regards to the expiry rule, we can simply set, like, for example, a value is considered expired if it hasn't been accessed for maybe more than a year, right? You can change this rule. So we answer our first question. What happens when a node or a value is expired, right? So for leaf node, we can simply replace the leaf node, expired leaf node, with the hash of the leaf node. Or for branch node, if all of the children are expired, then we can simply replace the branch node with the hash as well. So that's a relatively straightforward expiry rule. So for the second one, which is to revive, how can users revive the state is by perhaps submitting a transaction. Here we will introduce a new transaction type to revive certain state that user wants. So in the revive transaction, what user needs to do is to provide the key value and the period. If it's an expired leaf node, or if it's an expired branch, then they will have to provide a Merkle proof of some sorts. So yeah, we seem to be able to answer these two questions, but is this really the best solution that we have? If you really look at the before and after, it's not really that effective, because if you only look at the leaf node, you are simply replacing the value with the hash. And not just that, for all the values that we have in the try, we are adding an additional metadata. So in the worst case, we can actually have the opposite effect. Instead of reducing state size, we might have a scenario, in the worst case, where we are increasing the state size in size because of all this metadata. So this is not the best solution that we can have. Let's look at another solution. Instead of putting the metadata, the period, to each of the values here, we actually just put it on the branch node. So the expiry rule is similar, right? But here, for each child index, we are going to have the access period. And the concept of period is still the same. The concept of expiry rule is kind of the same as well. It expires when a child, it was considered last access, for example, a year ago. So what happens when a child is expired, right? Same thing. We replace the entire subtree with the hash. So just by looking at before and after, you can already see from the diagram, right? You are replacing a bunch of nodes with the hash itself. So we are saving up quite a lot of space. In regards to the revive part, it's relatively straightforward. You simply provide the path and the Merkle proof to the expired subtree. So yeah, it seems like a viable solution. GG easy. Seems like we got the best solution. And this is actually one of the solutions that BNB Chain raised last year. I was part of that team. We had a slight variance of this solution, but the core concept remains the same. But if this solution was truly viable, why hasn't they implemented it yet? Of course, there are hidden issues. One big issue is with proof size. MPT proof size is too large. So when we have large proof size, that means we will inevitably increase block size as well. Increasing block size will have effect on network throughput and network latency. So in the worst case where if a block is too large, then the validator couldn't process it in time, then we would make the network to become unstable and might potentially even halt it. So in regards to state expiry solution or MPT, from all of the solutions that I have right now, it's probably not viable because of the proof size. So we have to look for the next one. And thankfully, we have one, which is Verkle. So I'm not going to go through everything about Verkle. If you have no knowledge about it, you can check out verkle.info webpage to know more about it, or you can check out Guillaume's talk later in the evening. To go through the Verkle structure, right, you have internal nodes, which are similar to MPT's branch nodes, and you have extension node, which basically contains a group of values. Why Verkle is important, just to go through it briefly, it has small proof sizes, so it solves the problem that we have. It allows for stateless clients, it reduces hardware requirements, improves node syncing experience, ZK friendly, and more. One major change is that in Verkle, we are using a single tree approach instead of double layer. What this means is that we no longer have the concept of state trie and storage tries, but we put everything in Verkle tree. So without even understanding how Verkle tree works, you can come up with a state expiry solution as well. And we do the same thing by looking at the structure. What would you think we need to add in order to answer the two key questions that we have? It's simple. We do the same thing by adding the period to the extension node. Because in Verkle tree, one very special property is that values are grouped together. So because you have this very nice property, then it makes this solution very effective. And let's go through the flow like before. For the expiry rule, the concept of period is still the same. It expires when the extension node was last accessed, for example, a year ago. So we got our first question done. So what happens when an extension node is expired? It's the same as well. We replace it with the commitment of the expired node. The commitment, you can think of it as the same as hash of the MPT. Yeah. And in regards to the revive rule, what users need to provide in the revive transaction is to provide the path to the extension node, the period, and also all the values in the extension node. It's pretty straightforward. And this is exactly what we have proposed in EIP 7736, leaf level state expiry in Verkle trees. So it's a relatively straightforward solution. The advantage of this solution is, first, it's simple, relatively simple. Second is it has clear gas costs. The revive proofs are relatively smaller as well because you just provide all the things that you need in the extension node. And then it's also backward compatible with Verkle in the sense where if you choose to enable it together with Verkle, that's good, it's possible. But if you choose to enable this EIP after Verkle, it's also possible, right? So that's what it means by backward compatible. One major disadvantage is it only expires states partially because you can think of a scenario where majority of the leaf values hasn't been accessed for a long time, but there could be one single leaf value that has been accessed for quite actively. So in that case, the extension node is not considered as expired. So that's why this solution is called the partial state expiry solution. What if we want full state expiry solution? Well, we have to go back 3 years ago to Vitalik's multi-period tree approach, published in 2021. How it works is very different from the approaches that I've shown here. So you have the concept of multi-period tree. The concept of period is still the same. Here, what's different is that for every single new period, a new state tree is created. The expiry rule here is that the state older than 2 periods are expired. So for a client software, what they need to store at a time is really the state tree of the current period and also the previous period. Okay, for the revive part, it's more complicated than this if you look at the original article. But essentially, what we need to do is that given an expired account, for example, you will require the last known state tree of the account. Then you also need to provide the proof of all the subsequent periods up until current periods -1. That's a very simplified explanation. My problem with this proposal is that, first, it's super complex, and that's why I believe that the research in this direction has been stagnant in the past few years. Secondly, it requires something called address-based extension. So address-based extension by itself is already a very complicated and controversial proposal because it brings many breaking changes to our Ethereum protocol. So we are literally stacking problems onto problems. And secondly, what I can foresee is data duplication because you are storing two state tree at once. So in some cases, or even in the worst case, you might have duplicated data, which again, in the worst case, you can actually double the state size instead of like reducing it. So that could happen. And compared to the partial state expiry solution, you will have larger proof size because you have to prove different things now. So yes, we get full state expiry, but is it worth it? I don't know. The future, where are we headed next? So we know that for state expiry, we get slower state growth or even eliminate it. We get reduced hardware requirements, and we get a more efficient execution client. But to get those benefits, we exchange it for worse user experience because now users have to care about reviving their state. They have to submit another transaction in order to revive it, and those transactions will incur additional state revive costs, right? And another thing is that how do these users, like normal users, get those proofs from? Right? Well, the first part is definitely centralized providers. But we don't want to rely on centralized solutions. We have to come up with a decentralized solution, and that's why, in order to really enable state expiry while still providing a good enough user experience, we need a decentralized proving service, such as the Portal network. So yeah, and we might not even go for vocal tree instead. We might go for binary tree. So if we go for binary tree, then EIP 7736 wouldn't work. Depending on how the binary tree structure that we would want to go for, we have to rethink another state expiry solution. If it's similar to the vocal tree one, it will probably work. If it's totally different, then we have to rethink it. But if you follow through the thinking process that I've shown here, we can probably come up with a few variants. So yeah, by the way, Ethereum state just grew by 1.9 megabytes throughout this talk. So let's find a viable solution to state growth, and let's build an Ethereum that scales in time. Thank you.
Thank you so much. So we're going to go through the Q&A now, and we're going to go for upvoted questions first. So why do you need state expiry if you can have stateless clients in the future and have a smaller subset of nodes store the full tree?
Yeah, so in a stateless world, what will happen is that even with EPBS, validators will be stateless, then only block builders will have the full state. But even that, we are not solving the root cause, which is the state, the fact that 80%, for example, of the state is still considered as stale or hasn't been used for a long time. So statelessness doesn't solve this root problem, but state expiry does, right? We want to eliminate it. So in a world where we have stateless and state expiry, we can give a better experience to even block builders as well and make it more efficient. Yeah.
Great. Is state partitioning an option?
I think state partitioning is a general term. Like I need to know like in details what do you mean by state partitioning, but because I don't know the details, I will say maybe. Yeah.
And would it be possible to charge a yearly fee to the account if it has no ETH, delete the whole state? This would be a financial incentive for efficient state use.
So this is something like a renting model. It definitely is possible. But the thing about Ethereum is that if you are adding such a renting model, you are changing the entire economics. So it might break things as well. And in my perspective, I don't think the community would be ready or would support such a feature because it might break a lot of things. And economic-wise, it's also might not align to their incentive. So it is possible, but it's a social problem. Yeah.
And how about using snarks to compress proofs for revivals and do batch revivals?
That's possible. But again, in regards to how we want to use snarks, it really depends on how we want to change up the two key questions that we have. Like first, how do you want to measure state? How do you how do you know if a state is expired? And secondly, how can we revive expired state? So here, you seem to answer the second question, but how about the first? We have to explore that, yeah.
And the next one is kind of a question. Only write will alter the
Extension node?
X
Yeah.
node, no, not read?
In our proposal, yes, because if, for example, if a read operation changes the period in the extension node, you are essentially doing a write operation. So if you are doing something like that, you have to change up the gas cost for that particular read operation because it's read, but it's actually write. So there are a few proposed solutions. For example, if it's the first read in the new period, then we consider it as, for the gas cost, we consider it as the same as write. But yeah, there could be potential other solutions as well, yeah.
What would be the incentive of running an expired state provider node?
Expired state provider. No. So I'm guessing is that you have to provide, you're running a service that provides the proof. Honestly, there are no incentive unless you're running like if you're a centralized provider. That's why I say we probably have to rely on a decentralized service, portal network, perhaps, to be able to provide those proofs to everyone. Yeah.
Good intro to the next talk. What was the 20% state churn measured on BSC or mainnet? And if mainnet, have you tried measuring beyond 14 million?
Is Ethereum mainnet measuring beyond 14 million? No, because my node crashed.
Are there any gas refunds at state expiry and gas costs involved while recovering state at a later time?
In regards to funding, we haven't explored it yet, but yeah, that would be a good direction to look at. Yeah.
How about archiving old state compressed in cheap, slow storage instead of expiring it?
If you're talking about like a client implementation level, it's definitely possible. But if you're talking about protocol level, I foresee there are plenty of attacks that can occur. So I'm not too sure about this direction. Yeah.
Who is responsible for reviving an old expired value?
From the hindsight, it's going to be the users. But if you have like a sponsorship kind of model, then the sponsors can revive it for you, account abstraction thing. So yeah, that would be ideal for the users. But by default, I guess the users have to revive it themselves.
And where does a node fetch a subtree from when reviving it?
From some centralized, or for some provider, not centralized provider, sorry. Yeah, from some provider, yeah.
Perfect. Thank you so much, Han.
Thank you.
And we're going to have a short break until the next talk. So next up, we have somebody who I'm actually really excited to tell you came up from the Ethereum Protocol Fellowship Program, and he's working on Portal Networks. Please welcome Colby Moraz-Liebel.
Hi, I'm Colby Moraz-Liebel, and I wanted to give a talk today on decentralizing access to Ethereum utilizing Ethereum's portal networks, which might sound a little weird, but it will make sense through the talk. So the origins of Ethereum is was creating a programmable blockchain or a world computer. Instead of just having a simple ledger or colored coins, which were basically like coins with random features, you could program many features. And Ethereum's emphasis on this was decentralization and censorship resistance. But how did people access Ethereum? This was done through full nodes, which provided you a gateway to the Ethereum protocol through the JSON RPC. Full nodes were often long-running processes because if you turn off your laptop and turn it on, you have to resync, which is kind of hard if you want to send a transaction. You have to wait a few hours. So full nodes weren't always inaccessible. At the start, you could spin up a node very fast, but then as requirements grew over time, it became harder. I would say one of the greatest inaccessibilities to Ethereum is knowledge. Being able to run a node is a feat which all of us in the room can do, but can your grandma do it? And if for Ethereum to be accessible, you need it to be like, you don't want to run this thing, but you need to know something. Time, you need to sync a node. As I was saying, like if you turn on a laptop, like on and off, syncing a node to send a transaction is very unreasonable, and the IT costs associated with that. Updating your node for hard forks is kind of annoying when it's like repetitive every year. And then the biggest one, I guess, is hardware costs. It's projected in the next 4 months by ETH stakers that validators will need to update to 4 terabyte disks. And my little picture of like the man holding the world, which is like a Geth node, it's like pretty sizable and really annoying that you need to buy a SSD just to use Ethereum. So because Ethereum was inaccessible, this created a way for centralized providers, which took down the barrier of entry to access Ethereum, but it came with this consequence of centralization, which earlier when I said the origin, it's something we didn't want. So with one of the main concerns being the storage requirements, there is this nifty thing called ETH44s or history expiry, where in the purge path, this is basically, what if instead of all nodes storing all the data, we lowered the costs by not requiring them to store old data, what's no longer readily needed to run a validator. This doesn't mean nodes can't store the history, but it means they're not responsible for it all. But how do we achieve ETH44s? And enter the Portal network. What is Portal? Instead of depending on full nodes, which hold all, like the whole pie of data, what if it could only hold a slice of that data? Portal distributes this responsibility amongst numerous small nodes what are independent of each other. So you could think of it as like a slice of a pie, but the whole pie is still accessible through Portal. Portal is also sustainable. It's both a server and a client, which is very important because this problem has been here for a very long time. Previously in the past, there's been attempts at this, for example, LES, which the concept of it was an altruistic full node would host the server to a bunch of light nodes. But the problem that occurred was there was a bunch of users who wanted to run a light node, but not enough people who wanted to run a full node, so they were all overloaded. Portal switches this up by making all the participants contribute back to it, so it's sustainable into the future. We also get the benefits before as having lower storage requirements and lighter CPU usage. But how does this work? Portal uses a fundamentally different peer-to-peer model than Ethereum today. through distributed hash tables. Distributed hash tables enables decentralized storage and lookup system where each piece of content is addressed by a unique identifier and stored in multiple nodes for redundancy. DHTs make it possible to be able to look up the data even if you don't store it yourself, which is what I was going by when I said you could store a piece of the pie but still have access to the whole thing. And as I was saying, a totally different peer-to-peer model, Portal is also a replacement for the legacy Dev peer-to-peer network. In that, imagine Dev P2P is this triangle where you have to participate in everything to access anything. Portal breaks this up into different networks. One of our first ones, what we'll be launching, is Portal History, and then there's others. But what does each network do? Portal History contains headers, bodies, and receipts. Portal State allows you to access the state, such as your balances and contract storage. Portal Index is if you want to find which block body your transaction's in, and the Portal Transaction Mempool will be very interesting with Verkle and stateless clients. Currently, there's no hard solution for how we'll handle sending transactions in a stateless world. And we believe that Portal is in a unique position to solve this problem, and we will solve this problem. But anyways, with having access to all that data, you also gain access to a full archival node, but like distributed trademark. And the cool thing about that is it's like you can basically run a Portal node and have instant access, which is massive because in the past, if you wanted to have full archival access, which was provable, you would need to run a Geth node. But to run a Geth archival node, that requires 20 terabytes of storage, which is massive. And it also takes like over a month to sync, which if you just want like quick access to this, to archival Ethereum data, that sucks, especially if you're a researcher and you just want to research stuff instead of waiting a month to start your research. So Portal is fully provable, which is huge. There's kind of two paths to do this. So you could use our Portal Beacon network, which will be very useful for wallet use cases, where you could basically put Portal directly in place of a centralized provider. Portal Beacon Network is an implementation of the consensus layer light client protocol, and it will be integrated in any implementation. So if you want to use Portal, you don't need to think of anything else. You just integrate our libraries, and it's proven. A big use case, though, will, as I said before, will also be for full nodes. And for that, they're already running an Ethereum consensus layer client, which they can just repurpose to prove this data. So as I was saying before, there's all these Portal networks, but is there a dependency to prove? And there is. So for state, if you wanted to get your balance, you would get a proof to the state root, which would be in a header, but how do you know the header's real? There's accumulators in the Beacon network, like consensus client, called historical summaries, which is in the Beacon state. So depending on your use case, if you only needed historical data, well, then you would basically have this two-node dependency. But if you needed state, you would have an additional one. And by doing this, you only need to run a Portal network of what your requirements are for the use case. How do Portal clients initially get the data? Currently, it's through bridges. Bridges are basically full nodes which have access to all the data. But as Portal gets adopted in execution layer clients, which I probably can't talk about it, but like an announcement on the way. But anyways, so execution layer clients already gossip blocks around the network. Portal is kind of the same in that execution layer clients will be able to gossip blocks around the network, but they'll only need to gossip to a select few peers, where if they have 50 peers, now that nodes only store a slice, they'd only be required to gossip this data to maybe 10 or 5%, which saves bandwidth. Incentives. So why would people want to run a Portal node? Well, financial incentives are hard. It leads to a race to the bottom, and it's very easy to game. In that, let's say I want to maximize my income from running a portal node, well, then I could offer the worst service, but also allow for the most whatever metric you use to reward people. There are other projects trying to achieve this approach, and wouldn't it be really cool if everybody could participate in Ethereum's protocol for free? Because I don't want to pay someone to send a transaction or pay someone to get my balance when I open my wallet. We believe that Ethereum's protocol has innate value. That innate value is being able to send money, fetch your balance, use L2s, and Portal gives you access to this on cheap hardware. So if the value of Ethereum is high enough and the cost of running a Portal node is so minimally small, we think the incentives are aligned for people to run these nodes. Use cases, as I said earlier, lighter full nodes with storage requirements increasing, being able to add 4.4s while maintaining current day UX. If you just implemented 4.4s, your node would have no idea of what the past history was. With 4.4s, your execution client, it would be like you could fully respond to any request, and it would be like nothing ever happened. Another thing is nearly instant sync times for full archival node access. And the other is a replacement for centralized providers in use cases such as mobile wallets, which is pretty cool. But what's the catch, you may be asking? I'm selling this solution what seems too good to be true. So the trade-off is between latency and storage. Nothing is as fast as having it on disk, but for most of the data, you don't actually need to access it that often. So we believe that the trade-off for a majority of use cases is correct, is like actually there. And like the only time you really need quick access is if you're block building. And for mobile wallets, if it's fast enough, it's good enough. So for the first time, you can choose how you participate in Ethereum's protocol. I think this is kind of analogous to the infinite garden analogy that is often told on Ethereum's future. Instead of basically running a full node and requiring everything, there's tons of possibilities how Portal can change how you access Ethereum's protocol. Whether it's only subscribing to a few parts of the protocol, only history, or accessing the full protocol, it's finally a choice instead of a requirement to handle it all, which is, yeah, really annoying. Who's building Portal clients? Well, the Ethereum Foundation has been at the center of this from the start, but from the start, we have also been assisted by Status and Ethereum JS, which has been massive. Recently, Nethermind has been taking the stage, and for execution layer clients, they have been working the hardest on this from pretty recently, like last year, which is really cool. There's open source teams from around the world who are building clients. Another client's being built by EPF members, and I guess you guys could build Portal clients as well. We have clients being built in all these languages, so if you want to use Portal, you can. I'm sure everybody would be like happy to answer questions, and I think we covered like the whole stack, which is cool. Portal history is ready for developers to start using, and we have the data to back that up. So we built a statistics platform for like seeing if our stuff works, and we call that GLaDOS. For the past few months, we had 0 failed audits on our network, and what that means is the data is available on the network, and there hasn't been any case where we couldn't find it. So the system has been robust for months, and that's really exciting. There's a QR code there, but you should be able to find it on our website as well. Another exciting use case I was talking about earlier is wallets. We're building Trin Desktop, which is hoping to target everything but the browser. So hopefully, like Ethereum JS does that for us. Here's the front screen. You turn it on, and it's like, woo, stats. But you can also do ETH get block by number, get block by hash. get balance. But in the next few months, we're hoping to integrate a wallet, as we want to be like the test bed to show people this actually works. And what better way to do that than do it yourself and show people? And it's also, as I was saying earlier, you can configure your storage requirements. So if you set 2 gigabytes, you'll only ever need to contribute 2 gigabytes. You won't need to buy a disk in a year, which is really cool, because it sucks to buy a 4 terabyte disk when you already bought a 2 terabyte one. So now anybody can participate in Ethereum's protocol. As I was saying earlier, you could just integrate that into a wallet, and the user doesn't have to know it's running, which is really cool. And where to find out more, we have a QR code for our Discord invite, which is really useful if you want to ask questions. We have our website with guides and blog posts and how to set up most of the clients already. We have a Twitter, which our team hates Twitter, but it's good for getting people to know stuff. And then we have specs. So if you want to contribute, every team is super open to it, and they'd be super happy. We need to improve our issues a little bit, but that can be fixed. And yeah. So thank you for coming to, I guess, this talk on Portal. And yeah, thank you.
Okay, so let's go through some questions. I'm going to read them for you. Can I use Portal Network today to check my balance? If not, when? Same question for doing an ETH transfer.
So you can check your balance if it's within the first million blocks. So if you guys used Ethereum 9 years ago, you can check your balance today. We expect balance for latest account for checking balance for the head to be available in Q1 or Q2. We just need to finish some infrastructure to support that.
What is the biggest hurdle to getting all clients to adopt the Portal Network, and how can the community help Portal get adopted?
I would say the biggest thing has been awareness. 2 years ago, people were like, what, Portal? And then it's a minimal implementation. And all these questions, what never really made sense. But especially this year, people actually know what Portal is. And it's really cool to see people referencing Portal, actually about it. And we don't have to do all the talking ourselves. So I think just talking to people about it is awesome.
Awesome. What is the minimum percentage of network data that a Portal network is expected to have?
So we have thrown numbers like 100 megabytes, but that's fully configurable. Since the requirements are so low, for our client at least, we wouldn't be surprised if we set it to 1 gigabyte, because realistically, someone wouldn't notice. Most apps are 500 megabytes on their phone. So it's if we use a gigabyte, they probably wouldn't notice. But it's configurable.
And I think the next two questions can be combined. How does Portal Network compare to classic peer-to-peer file sharing networks such as BitTorrent?
So one of the problems with BitTorrent is it doesn't have an inherent way to prove the data or validate it. So you run into problems of you need to download this huge section of data, and it's very uninformed. Portal is different in that all the data you can fetch from the network is provable. So it's much easier for a client to, let's say, fetch any piece of data they want, where through torrent, they would probably have to index this data and do some kind of out-of-band proof, which would be a lot more complex and have a much worse UX experience.
And you answered this one in your presentation, but it was asked before. So is there incentive model for running a Portal Network node?
For writing a Portal Network node, I guess if you wanted to use it in your wallet and you used a language what wasn't there yet, I guess that would be the incentive. Accessing Ethereum with instant sync times, decentralized, very cool.
Could one implement an archive node using Portal as a backend?
Yes. So the idea is Portal would have all the data that an archival node would have. So you could just use Portal as your archival node. It would be a little slow, but you could.
What are the expected hardware and network specs in gigabits for running Portal nodes, and who do you think will be ready to operate these altruistically?
I think that the top 3 execution layer clients would be running all these, so by default. So that's a lot. Other than that, like if you're running a wallet on your phone, I guess that's like that's not really altruistic. You have actual utility in that. So I think we can do quite fine while ignoring altruistic use cases.
Has there been engagement with IPFS community? It sounds like there's a lot of overlap with DHTs, accessing content, address data, et cetera.
So some of the issues with IPFS is since they have no validity scheme, one of the things is data is constantly cycled off the network. And because of our strong validation conditions, it basically means if we have enough storage, it's on the network and it won't be flushed off, which is really important for the longevity and robustness of Portal, which isn't there with IPFS. Also, they use TCP, which has much higher latency, where I forgot to mention our talk, but we're based off Disk V5, which is the current day node discovery protocol for Ethereum. And it uses UDP, which is much quicker for like getting responses back. And especially like if you have to ping multiple peers, that adds up.
Don't some nodes need to sacrifice for Portal Network or in Portal Network for this to work? Not lots will run archival data, but lots may query it, and these might get spammed.
So a Portal node would only need to hold a very small slice of the data. So if a full node is only like storing like 1 gigabyte for Portal, they probably wouldn't really notice it. There is no real requirement that they like store all the archive on their node. The idea is that all the like full nodes on Ethereum store like way less, and it's like they all contribute. Where currently it's like every node has to store all the data. What if we did this a little like more smart, I guess?
What are the guarantees that the data will not be lost over time?
I think the guarantees is kind of analogous to what I said earlier about validation. Any storage we have above the minimal requirement is used for redundancy. But if worst case scenario, there's other archival solutions. Portal is really good for accessing the data, but in a worst case scenario, you can use archival formats such as ERA or ERA1. So the data wouldn't be lost if it wasn't on Portal. There's optimized formats for archival. Portal is really good if you want to access it.
What is the most resource-constrained device that has been appear on Portal?
For us, it's basically been, I guess, Raspberry Pis. I know Raspberry Pis have gone a little strong, but I don't, like, when we run it, we don't even use a core, and we use like 300 megabytes of RAM. So like, something with maybe like 500 megabytes of RAM would be fine to run Portal on. And we haven't even optimized it yet.
Does Portal support WebSocket connections?
Through the RPC, that would be dependent on the implementation. Ours does, but it's, I guess, the implementation's choice.
Cool. Can we get another round of applause for Colby? Thank you so much.
That's so good.
And we'll be back in 5 minutes with POTUS on
Thank you.
ePBS. everybody. So our next speaker is one of the most vocal people on the All Core Dev calls and on Twitter, and we're very grateful for him for doing that with the All Core Devs. This is POTUS from Prism talking to you about the status of ePBS.
Thank you. But just in my defense, I opened my Twitter account only to pitch this, and as soon as this is shipped, I'm going to shut up on Twitter. Anyway, so today I'm going to be talking about the status of ePBS, and ePBS during this talk is going to mean enshrined payload block separation. This is not the usual meaning, and you'll notice that I'll only mention proposers and builders towards the last couple of slides. The talk is going to be divided in 3 sections. The first section, I want to convince you for a while that dividing the payload, the execution payload from the consensus block is something that is necessary in Ethereum. It is highly beneficial. It is a scaling factor, and it enables other scaling solutions like PRDAS to actually fulfill its full potential. We have this problem that we have since emerged, which is our tech debt, that we adopted this minimalistic way of merging out of proof of work, in which we included the execution block, the one that has the transactions and everything that we need to modify the Ethereum machine, inside of the consensus block that has the attestations, the deposits, the exits, everything that we need to decide what is our current head, and we distribute them both together. This makes for a large chunk of data that is distributed among the nodes, when this data has logically different purposes and logically different validations. What a node does when it gets a block, it needs to get to consensus in 2 different things. One thing is, what is the status of the network? What is the execution status of the network? The validity of the block. And the other thing is, given 2 different views of the network, which one, even both of them possibly valid, which one is the one that we consider the head of the chain? These 2 validations are completely independent, and they are done by 2 different clients, even 2 different pieces of software the validator runs in the computers. The execution consensus is about validity. The consensus is about which one of the viewers of the world, is the current one. Because of our tech debt, the way that we validate blocks puts all of the strain of the network in the very first few seconds of the slot. A block is broadcast at the beginning of a slot, and it needs to be validated. It needs to be downloaded entirely by the whole network, and by 4 seconds, validators need to have already checked consensus, executed the execution, checked that the block data was available, in the future checked that the inclusion lists were satisfied, and attest for this. The rest of the slot is useless time, essentially. We're just counting attestations, aggregating them. The node doesn't do anything. If anyone here runs a node, you're going to hear the fans going off exactly every 12 seconds. So that's what the Ethereum validation is today. And the question is, can we make this better? Can we make the timings better? Presumably, yes. We have 4 seconds, and actually we don't use those 4 seconds. But the problem is that validators are incentivized to actually propose their blocks as late as possible so that they can extract more MEV out of them. And these timing games make twiggling with these timings for attestations an impossible problem to solve. If we gave more time to actually sync better blocks, larger blocks, have more blobs in the network, what would happen is that validator would just propose later and extract more MEV. So why separating them? Since we do not need to validate execution to decide what is our head, why not just broadcast the block, which is a minimal block, which is just consensus, validate consensus, decide what is our status of the chain, and then use the rest of those 12 seconds to validate execution, check if the blobs are available, validate inclusion lists, do all of the stuff that is actually heavy in the high latency path. And the low latency path, which is validation of consensus, that takes 2 seconds, you just download the tiny block, validate it immediately. It takes 70 milliseconds today to validate the consensus side, and just attest. So that's that's a scaling feature of separating the payload from the block. So that was the first part of the talk. I hope I convinced you that the separation gives us a lot of benefits for Ethereum. Now the question is, how can we achieve separating the block from the payload? And the minimal features that we need if we want to separate them would be this. So what's what we desire of such a separation? We would want to have these validations done completely independent. We want to validate the consensus side in the fast path and the execution side in the slow path. We want to separate the propagation of these two blocks. The large chunks of transactions might take longer to come. The blobs, that are the huge chunks of transactions, might take longer to come. We do not need to have a very high uplink bandwidth to submit the blobs because it takes 12 seconds to be disseminated. So we solve the bottlenecks that we have today in things like peer DAS or full DAS. And we see immediately one problem, and is that, well, since now you cannot sign the block with the payload, because otherwise we will have a free data availability problem, we need to have those two objects being signed. That's it. That's not so hard. Verifying signatures is not a problem. Here's the real problem. The real problem is that now, whatever the situation, whatever the design, the mechanism designed to separate the block from the payload, you will have to deal with new features, with new situations. Today, a slot either has a block or it doesn't. Those are the two possible status. If you have a consensus block, you have a payload, and if you don't, well, you don't have a payload. But in a situation in which you have validated the block, the consensus block, you attested to it, and it's your head, and the payload might be invalid, or might not come, or the blobs were not available, or it didn't satisfy an inclusion list. The situation is that we have one extra status, which is the status in which the consensus block was valid and the payload was not. And this gives a problem, which is a forward choice problem. You need to change forward choice to account for these statuses. You need to check that if I attested to a block whose parent did not have a payload, well, that attestation does not count towards a parent that did have a payload. And this is completely independent of any auction mechanism. This is the complication of forward choice. Of course, you need to still provide security that you're not going to be rewarded for free. But anyway, so in such a world, the other complication that you have, that client implementers will have, is the fact that we have it enshrined in our coding that we get the block, we validate in certain order, we can validate in parallel execution and consensus, and we all do, because the validations are independent, but then we wait until both validations are done, and we attest. Now, one would naively think that that's easy to separate, because you just send the things that we're doing in parallel, just validate consensus, attest, and then validate execution in the rest, and that's it. But that's not so easy because, unfortunately, the merge was minimalistic, but then we had Capella. And in Capella, we added new messages that came from the consensus layer to the execution layer. In Capella, we have withdrawals that are deducted in the consensus layer, and then later on are credited in the execution layer. If we have them separated, we're going to have to do that logic. Deduct first from withdrawals, and then credit on the execution layer when we see a payload. So that's a complication. And Electra gives us many more headaches. Now in Electra, we have messages in the other direction. And in future forks, we expect to get more and more messages in the direction from the EL, triggered in the EL, towards the consensus layer. These are, for example, deposit requests, withdrawal requests, and so forth, which you will have to change your code in such a way that when the payload comes, you process those. Okay, so the point I'm trying to make is that the complication has nothing to do with neither MEV and the auction mechanism. So now we're going to start moving to auctioning. But before that, let me tell you what the slot will look like in a way in which we separated the payload from the block, regardless of auctioning mechanism. We will have a broadcast. You're going to have to validate quickly execution, which is fast, and then you have the rest of the slot to just get consensus on whether or not the payload was there. Okay, so that was the part of payload block separation. Now we come to the section of proposer-builder separation. So I've described the problem, the big lifting of separating the block and the payload is in two sections, changing forward choice to achieve consensus on what is the head of the chain, and changing clients' implementations on how they sync their block, because they need to do things in a essentially different way. They need to access the databases in an essentially different way. But now the question is, well, how do we implement this? How do we achieve an implementation that separates the block and the payload in a minimalistic way? And I want to convince you, well, which is probably hard, but I want to make a case that with minimal assumptions, EIP 7732 is a system that achieves this in an actual minimal way. So we need to decide a way of how the payload appears. And I'm going to talk a little bit about auctions. There are many ideas going around. They all have acronyms that are hard to remember. EPBS, slot auctions, APS, ETs, ATs, I don't know. But they all more or less are in the same way. There's someone that sells a right to produce a payload. In block auctions, the proposer submits a block, a consensus block, with a commitment to a particular payload. And the builder that's committing for that particular payload promises to pay a value for the rights of producing that payload. In slot auctions, the proposer does not commit to a particular payload, it only commits to a particular builder, and then the builder later on produces any payload that he wishes to produce. There's execution tickets or execution auctions in which the auctioneer is not a validator, but it's the protocol itself. The protocol sells far in advance, 32 slots in advance, either tickets, and then there's a lottery that is run by randomness, and we choose who later, 30 slots later, who proposes the payload, or you can actually sell. The protocol can sell, can hold an auction, and sell the rights to propose a slot, 32 slots in advance. And all of these mechanisms have their trade-offs. None of them come for free. All of them impact the MEV chain, and all of them produce different kinds of centralizations. All of these mechanisms that I'm describing here, you can or may not run them with MEV burn. That means that even if the proposer is choosing and getting some value out of the builder, you could, in principle, include a burning of that value towards the protocol. The one that I didn't include is no auction, but that's certainly possible. We wanted to set, it was about enshrined payload block separation. In principle, I could just enforce that the proposer is the same signature as the builder, keep everything exactly as it is today in the MEV chain, and keep using MEV-boost. Nothing would change except that we have all the machinery to separate the block and the payload. However, if we've already did the heavy lifting, which is changing for choice and changing block processing, changing the auction is zero work for us. Changing the auction is nothing because the auction, we already have it. We have the code that requests header from the builder. We don't need to change that. The only thing that we need to check is that the signature will be different. It's coming from a particular validator. So the heavy lifting is done in a minimal way, and adding an auction to get block auctions is trivial. So what are the things that actually change? The problems that adding the auction increases is that in a world in which the proposer and the builders may be different, then you need to give certain safeties to the builder. If the proposer and the builder is the same, then you don't care about protecting the builder if the payload came late or if the builder wanted to withhold the payload. This is because, well, the proposer is the same as the builder. He should have sent everything together. But in a world in which the proposer and the builder are different, you need to protect the builder. You need to give assurances to the builder that if the builder submitted his block on time, the block is canonical, the payload is canonical. And you need to give assurances of a hard one. It's a new situation. This was a previous slide where the three phenomena could happen. This is the block was full. Here, the proposer of slot N is building on top of an empty slot. Here, the proposer of slot N is reorging entirely the previous block. But now we have a new situation in which the proposer of slot N is trying to make the builder pay for a payload that he didn't reveal because the previous block was weak. So we need to prevent that situation from happening, and this is a minimal change, luckily for us. EF researchers on for choice are very good, and we have minimal solutions for this that add a tiny bit more of code to the previous heavy lifting, which is dealing with the whole tree. So how does the EPBS slot actually work? on an auction mechanism, the builder, the proposer at the beginning of a slot requests, exactly as with MapBoost today, with the exact lines of code, will request directly from the builders, not the relays, their best bid. It would choose whatever bid he wants, it would include it in the block, and submit its consensus block that can be validated immediately before 3 seconds. We could have been 2 seconds, actually, because we don't need time to propose blocks, consensus blocks. The rest of the slot, well, the builder will now have to be protected, is going to count attestations for that block. It's going to count for 1 second until he reaches enough attestations. In practice, it's going to be 40% of attestations. Once the builder saw 40% of attestations for the block, the builder knows that that block cannot be reorged. Therefore, the builder reveals his payload. This is 4 seconds. So you have since then until the very next slot to validate the payload. You can just increase the gas limit a lot if we could manage to solve the state growth problem. You can increase the blob number a lot, because now we have 12 seconds to distribute the blocks. You don't have 2 seconds to distribute the blobs. Later on, there's a light vote. There's a light vote by a committee of 512 members. And that vote is to signal the rest of the chain that the payload was on time, that the next proposer should not reorder the payload. There are other designs that do not include a light vote. There were previous designs that included a full vote, an aggregated vote, an attestation of the whole committee for the payload or not. But this design is robust enough, and it requires only 512 signatures. So let me tell you about implementation statuses of, I'm not sure if I can, yes. It's an empty video, but let me tell you about implementation status of this. So we wanted to have a proof of concept model for ePBS, and we have it. We are finalizing ePBS, locally constructing blocks, so we're not contacting a builder, but we are finalizing a network that has the payload and the block separated. 2 consensus clients have already the implementations underway. Teku, I believe, is close to being an interop. Nimbus has 2 EPF working on this. Lodestar and Lighthouse, I think they initiated, at least they have the typing, but they haven't advanced much more. But the point is that it took us a couple of months of sitting down and coding, not more. It's not production code, but it's certainly ready. The EIP is ready to go. As I described, there's no changes. I'm only mentioning consensus layer changes. There's no changes on the execution layer. That's why the execution layer guys are happy, because we're going to give them a lot of time to validate the block without them writing a single line of code. However, the interaction with Fossil is not trivial. If we want to include inclusion lists, which is something that we really need in Ethereum, we're going to have to involve the execution layer. And the interaction of Fossil with ePBS is not entirely trivial. It's not something that I'll describe today here. All right? Thank you very much, guys.
All right, we'll go through some questions from most upvoted. Are there any other protocols or message propagation mechanism being explored other than libp2p?
Not that I know.
Simple answer. After implementing ePBS on Prism, how would you rate the complexity of changing the entire consensus execution validation, sync, et cetera, while still maintaining backwards compatibility?
That's a great question. It was much harder than I thought. For choice was the problem. And, but we have now because we iterated several times until we realized what is the right way of doing it. So now, backwards looking, there was a very simple way of doing it. So my original implementation was hard, but now we have a very simple change. As I said, in 2 months, we did it. Now I believe, knowing what is the right design, we could have done it in 2 weeks.
What if there's a reorg larger than depth of 1?
Nothing changes. Absolutely nothing changes. For choice, my original design used boosts to rely on if the block was poor and the builder did not want to reveal the payload, my original for choice design relied on the network reorging the whole thing. Luckily, Francesco came up with a simplest solution that doesn't touch for choice at all. It's the usual LMD ghost mechanism without any boosts. So for choice is not different in the way that we count weights. The only difference is in the way that there are nodes that may or may not have a payload.
What do you think about implementing consensus execution separation without ePBS?
I think that the way I phrase this talk is that there's a big chunk of changes that are completely independent of any kind of mechanism for auctioning, and those changes are going to have to be included in any known roadmap for Ethereum. In all of the known roadmaps for Ethereum, we have this separation between payload and block, and that's the heavy lifting that has been done. Now you need to put on top of this an auction just as an implementation detail, and the reason why we chose block auctions is because I do not know how to implement any of the other ones. And if anyone gives me an actual spec to implement execution tickets or future slots without single slot finality, I'll be happy to code it. But these are the only two that we actually have a spec, and we know that it's robust and safe.
What about the impact on the late block of proposer boost?
What about could you repeat that one?
What about the impact on the late block of proposer boost?
I'm not sure if I understand the question, but so perhaps, so the question is perhaps that if a block comes late, proposer boosts can reorg it. Yes, and this is something that we do today. Today, in order to not incentivize seeing late blocks, we actually have seen blocks coming in the early days at 12 seconds, trying to reorg the next block. In order to not incentivize this, we actually actively reorg a block that comes late, and that's not going to change here. The only thing that is going to change is that the builder has a safety mechanism that if the block came late with a commitment to its payload, then the builder may not reveal it because he knows that it's not going to be forced to pay, because it has to be reorged.
Does this proposed change require an ETH spec change or an EIP, or does it only require client implementation changes?
It is a consensus breaking protocol. It's not backwards compatible. It requires an EIP. The EIP is 7732.
We have 2 more minutes, so if anybody has a live question that they want to ask.
Oh, that's a great question.
Can you repeat the question real quick?
So the question is whether or not if we've implemented sync. No, I have not. Purposely, because I really wanted to have the proof of concept before Devcon. Nothing really changes though, because for sync, what you can piggyback what we already have today. So for sync, you're going to send the full block together.
Any more?
Are you afraid that given the changes and introduction of new features of the off-chain PBS pipeline, we are soon going to reach a point of no return where ePBS is pretty hard to even be realized?
I'm not sure. I'm not sure I understand the question. I'm sorry.
For example, when PBS started, we had the relayers just do one thing, but then we did stuff like optimistic relays. Recently, there have been proposals of stuff like gateways, which again relays do. So we keep adding complexity into the off-chain PBS stuff that would need to be matched or improved within ePBS. Is this a problem that you see or foresee, or is this a viable risk for you?
I don't see this. I can tell you something that I see as a risk. I don't see this particular thing a risk because complexity on the relay, all that it will change. What ePBS, the way we're proposing it, what it does is it allows the builder to be a relay directly, permissionlessly. So what you're describing to me sounds like builders in the protocol, which they already are because relays are builders. They will have to have this complexity if they want to be competitive in the market. But from the protocol perspective, we don't care. What I do see as a risk, though, is other things that are being piggybacked on PBS. Say, for example, pre-confirmations and all of these extra markets that are being done. I would ask for the teams that are working on pre-comps to make it compatible, forward-looking compatible with mechanisms of separation.
And if the person who answered the multiple concurrent proposer question wants to ask him afterwards, we're out of time for questions, but he'll be around in the room. Give a hand to POTUS. And next up, we're going to be doing ZK proving at the history of Ethereum in real time, and that will start at 12 o'clock. hello. So next up, we have the co-founder of Polygon, working in the ZK. He's been working in the ZK space for some number of years, and he's here to talk to you about ZK proving, the history of Ethereum in real time. Please welcome Jordi Bailina.
Hello, everybody. We need fast proving. At the beginning was we need proof. We need to generate proofs. At some point, we need to generate cheap proof. This was the beginning of the ZKVM. But what we are seeing now is that no proofs are, I would say, that's cheap enough, especially if you are doing a roll-up and you have the transactions, but we need to prove them fast. Why we need fast proofs? I would say for many reasons. The reasons, I mean, in Polygon, for example, we need it very much for the ACK layer. When you want to transfer funds from one chain to another chain, two things needs to happen. First, you need to, one chain needs to commit to one state so that the other chain can use the funds of the first chain. And the other thing is that the second chain needs to be sure that this state is correct. Okay? So it has two options. The first thing is that the second chain just follows that chain and then guarantees that this state is correct. Or the other option is that the chain A provides zero knowledge proof that his state is correct. In the first case, well, it works well maybe if you have two networks, but if you have hundreds or thousands of networks that are appearing or disappearing every time, it does not scale well. I mean, you cannot ask all the validators of all the chains to run a validator of all the other chains that are in the aggregation space. So the way to scale that is by having a zero knowledge proof that guarantees that the state is valid. This is, but then this means that the user, when he's doing some interchain communication, in the user interaction, I mean in the UX, you will need this. You need to wait for this time. Okay, so we need to generate these proofs as fast as you want. Other context, I mean, yesterday in the presentation of the Bean chain was a ZK chain. So that means that in this context, you need a lot of places. Like clients needs to validate, so needs to prove that the full execution chain, it's another case that's important. So in many cases, this chain, so generating fast proof is important. So how fast can we go? And I want to present here, so an internal project that we have been working for the last 5-6 months inside Ethereum. We call it internally ZISC, and it's very much about that. It's how much we can push the proving system. ZISC is also based, it's a system that can prove, I mean, you can build a program in Rust. It's a RISC-V compiler. It's a RISC-V 64 bits. It's a little bit different from other projects. But the full idea of this project is how fast can we move? How fast can we generate this proof? These actually are these three different, I would say, three different pieces or three different projects itself. One is the prover itself. A prover is a generic prover. So the idea is that you can build your own prover that can prove anything. We say it's kind of the hardware layer. We have the PIL2. PIL2 is based on the PIL1 language that we use in the ZKVM, and allows you to do an arithmetization another way. We extended the PIL2 language, the PIL2 language. I mean, making them more easy for auditing this arithmetization, and mainly including one thing that's called VATCOPS. That mainly means that instead of having monolithic proof, we can divide the proof in subproofs. This is very important because then we can parallelize very well. So we have a proof, we divide the work in different subproofs, and then we aggregate them together. This is the main idea of how we can accelerate the things. Okay? So the prover, I mean, it's a generic prover. So how it would work? Okay? This is the process that if you want to build any proof, it can be from a Fibonacci series, if it's a kind of a hello world, until a VM project that's in there, or maybe whatever you want to build. Because mainly you need to build two things. So you need to build the arithmetization. The arithmetization is in this, so we just write the PIL. So it's arithmetization itself. You need to write what we call the witness computation. This is at the end is filling, it's a program that's actually filling the trace of this. And that's very much, and with that, you already have a prover. So with this, well, you compile the pill, okay? So you get a kind of a pill-out format. You get the Rust. You compile a library. I mean, you get a dynamic library, okay? From the pill, you get some helpers, so that allows you to build this witness computation easily, okay? And then here we just run a normal setup. Here the setup is the configuration of the prover itself, some Starks configuration. That's just a configuration file. Here we generate a normal approving key and a verification key, and then we have the normal thing. We have a prover. For the prover, has an interface that you get an input, and this prover generates the proof and the public outputs, and you can take the proof and the public outputs and verify in the verifier. Oh, you see, that's got it here. Okay. So this would be the schema that would work. Okay. Thing is that this prover is generic. I mean, you don't need to recompile the prover. It's just a program that's running there. But can be a program, can be a service, can be. I mean, this program. I mean, and this program can have like different versions. I mean, it can be in GPU. I mean, you can. It doesn't change. I mean, you can have. It's generic for any. The idea is that it's generic for any circuit. Okay? This program is. I mean, it's open source, and everything is designed to minimize the latency. Okay, we will see later the different things related to that. Okay, so and then let me just go back. So this would be the prover. Okay, but on top of the prover, we have a specific circuit. So it's just one. So we are using it's like the specific circuit using PIL2, and that's implemented in PIL2, and we can use the prover. That's actually this this disk is this let's say RISC-V emulator kind of. Actually, it's not. I would not call it an emulator. It's a ZK processor. The only thing is that there is a direct conversion between RISC-V or even WASM or other or LLVM to this ZK processor. It's a processor that has only about 50 polynomials, so it's very, very lightweight processor and really fast and really fast processor. Okay, so and then it works very much like any other VM in there. So you can build a program. So you build the circuit in a normal program. Of course, you can test your circuit. At the end, it's a deterministic program. So you compile the circuit, you get a program, and then you have an input and an output. It's a deterministic program that generates the circuit. Once you have that, that's the only thing you need. You can take this program. You can generate, I mean, you can compile using Rust and some setup, and then you get a kind of a ROM, or if you want an ELF kind of a program itself. And then you can use the prover, I mean the prover that we saw before. Of course, here the CISC, the private key, the verification key is already done, because this is a specific application, a specific circuit for the prover, but the prover is exactly the same. And then, of course, you have an input, a proof, an output, and the verifier. The only thing is that the input includes the private input and the ROM, so you can prove any program that you want, and of course in the verifier you can use the ROM hash, so you can use the verifier itself. Okay, so let's go deep in how this, I mean how the architecture, I mean how this circuit works. Well, as I told you before, this circuit is based on VATCOPs. Actually, there are many subproofs. This is subproof. There are different kinds, and this works very much like a normal processor. We have like a main processor with a program, with a ROM, and then we have a RAM, we have arithmetic operations, we have a lot of coprocessors that can be connected here. Okay, so each one of these is one subproof, and actually you can have, for example, arithmetic. If you have a lot of arithmetic operations, you can have a lot of subcircuits and all them add them to the bus, and they connect them together. This bus, I mean, it's not an electronic bus, but it's something, I would say, similar. I mean, it's more an algebraic bus. But this, we are using here lookups. And here the idea is you can have different subproof. So you can have the main processor, you have the arithmetic processor. Each one is like sending things to the bus. And the main processor says, okay, I'm assuming that this arithmetic operation is correct. Okay? And then there is the arithmetic coprocessor that's saying, I'm guaranteeing that this arithmetic operation with these values is correct. Okay, so the full system is correct. So one is adding to the bus, the other is subtracting to the bus, and at the end, the bus means 0 if everything is guaranteed. And the cool thing is that, I mean, in this bus, I can add arithmetic operations, I can add memory instructions, I can add whatever you want. We have a kind of identifier, but with the same polynomial, we are just adding and subtracting different things all together. Okay? You see the arithmetization. I'm not going to go in detail on the arithmetization, but I give you the big ideas. I mean, the processor is not based in registers. Registers in ZK are relatively expensive, mainly because in one instruction you are using in general 1 or 2 registers. So that means that there is, like, if you have 32 registers, you may have like 30 columns that you are not even using in that line. So doing registers in ZK is quite suboptimal. So the main idea here is, okay, we have like, so in each instruction, what we do is we go directly to memory. We are doing to access to memory. We are reading to things, and we are storing back to the memory. And in this, this is the main idea. Okay, so we have only one register. Actually, we have a couple of registers, a program counter, a kind of a frame pointer or stack pointer in there. We have this main instruction that can be any instruction there. So we have a way, this is a way to load the first register, load second registers. I mean, you can load from memory, or you can load maybe from an immediate value or other things. Maybe you can take just the previous C and things like that. Okay. We store in the memory. Generally, we store to the memory. We can also, for example, store to a program counter, so we can do a dynamic jump in there. Okay, and we have the operations. The operations at the end is just throwing to the bus the operation that you want to build. So the main state machine is quite simple in there. And then we have some conditional jumps somehow. I mean, all this logic there. So at the end, we are just, so the operations is A plus B equals C, maybe with a carry or with some flag where you can do a jump to one line of code or a different line of code. So this is a little bit the deepness, the big idea of the THISC itself. Okay, and as I told you, this goes through this bus. Okay, and one of the advantages, and I want to see here, I won't give you details about why this architecture is very optimal. For example, when you have a multiplication, so the CISC processor is sending that, and the arithmetic is also somehow proving that specific operation in there. Okay, so you can have this arithmetic operation. But one optimization that we can do is, okay, for example, imagine there are a lot of operations that are usual. When I'm doing, for example, 1 plus 1 or 3 plus 1, I mean, I'm doing small numbers. I'm going to do a lot of them in the processor. So instead of proving all of them in the processor, I can have another state machine that's kind of a cache where I have pre-computed operations that are used quite often. And then, so the processor is always it's sending the same thing, but then these basic operations can be proved back to the bus. So that means that for these small operations or for these usual operations, the cost, I mean the number of cells that we are doing are very low. Okay, can extend this idea. So we can have this processor. Imagine that I have operations. I can have a usual operations table. I can have operations that are doing, so a specific state machine that is doing 32 bits operations, and another state machine that are doing 64 state machines operations, just to save space. Okay. This idea of work works, for example, for memory, for the memory alignment. I mean, what I'm doing in general, most of the processors are doing reads and writes that are aligned. Well, no problem. The processor is doing some memory operation, and the memory that just works in 64 bits words. Then you're doing a read, aligned read, you get it from the memory. Aligned read, you get it from the memory. But what happened when you are reading an aligned? Well, we can have a special state machine that's solving these unaligning things, and actually it's okay, so you want a non-aligned operation. This solve, so the arrow to the bus means adding to the bus. The other arrow that goes in the other way is subtracting to the bus. So, okay, I'm proving this, but in order to prove this, I need to do 2 reads operations. And of course, some logic for for putting these two reads in the same way. And then, of course, the same memory machine is doing these 2 reads in there. This allows us to do these kind of techniques. It allows us to do, for example, continuations in a very easy way. So if I have a processor, I can divide the execution in different slots, okay, in different phases. Okay, so this is the first 100 clocks, second 100 clocks, and so on. So I can divide them, but at the end of the processor, so I need to connect. The next slot needs to have the same state that when I finish. Well, what I can do is just send this state to the bus and recover this state from the bus, and then connecting all of them together. Okay? The final one, the first one, this is because it's cyclic. In ZK in general, we were cyclic, and then disconnects. The same with continuations in the RAM. Continuations in the RAM, of course, is not time frame. In the RAM, you want more address phase. So I can divide the proof of the RAM that can be big in smaller pieces, but the idea is the same. I have a state transition function that goes line by line, but from the one chunk to the next chunk, I can send the state of the RAM to the bus, recover the state of the RAM to the bus, it's the last address that you are reading or writing, and then you can continue. So we can split also, for example, the RAM in there. So this allows us to divide all the work. There is no big state, so there is no state machine that you need the big thing. So you can divide always the work in everything. Okay. Here, as I mentioned, there is a direct conversion. This is important. Direct conversion. That means that you can use Rust or any other compiling language. It's 64 bits. When you can use Golang, or you can use C++, or you can use even Java. There is RISC-V 64 bits is quite standard in there. And as I told you, there is one direct conversion, one-to-one, from RISC to CISC. We also have a kind of a side project that we are evaluating, converting from WASM to CISC, and even directly from LLVM to CISC. This is perfectly possible, and it can be quite optimal, because when you go to intermediate code, you don't need these registers, and then you can have better code in the processor. But in general, the cost of the proof, of course, the processor is important, but I would say that the operations that are doing the processor are even more important in general. So also it's not that you are optimizing the processor and then you get a better proof. It's the whole thing that you need to optimize. Okay. CISC advantage, we already talked most of them. Okay, it's low latency, and we integrate with the recursor. We didn't talk about the recursor, but the recursor is the idea is that you can take any proof, and then you can build kind of automatically a proof that aggregates both proof. For example, if you are proving 2 blocks of Ethereum, you can get a proof that actually aggregates this proof. Okay, and we have this recursor that's the tooling that allows you to do that automatically on this. Okay, so latency. How we push hard on the latency. Actually, there is 4 pieces. I have not much time, but I'm going to try to go fast. The first one is the one that you cannot parallelize. Okay, it's like, okay, if I want to prove a computation, I need to compute that thing. Okay, so I cannot parallelize that computation very much. Okay, and also, if we are emulating, for example, RISC-V, I'm doing an emulation, so here I can go slow. But we are trying this to go as fast as we can. Currently, we are at 80 megahertz, so we can run a processor running, let's say, the minimum trace that you need then to generate the witness computation. We can go, I think that there is margin here for at least 1 order of magnitude improvement. Then we have the witness computation. The witness computation, this is already done in parallel, so this can be parallelized. Very much, and you can even start building this witness computation while you are executing that. Also, the witness computation, the idea is that we are doing that work in the worker. We are not have like a central prover. We can do that in the worker. That means that here we limit a lot the bandwidth. So we have one bandwidth. We don't have bandwidth requirements. It's minimal, the quantity of information that goes from the between the workers, or a central, I mean, the coordinator and the workers. Okay. Then we have the subproof building. Actually, this is the high work, but the cool thing is that because we have control of what's the size of the subproof, then it's just a matter of putting more subproofers. Of course, if they are cheaper and faster, you will need less subproofers. If they are slower, you will need more. And that's very much a matter of a cost, but not a matter of a latency, because we can control very much this proving time. Okay? And then the other last is, okay, then we need to aggregate. Okay? This is probably currently where we have the bottleneck, but I mean, the good news is that we are getting much, much, much better. And this number, 10 seconds, we already get lower to that. Here, as mentioned, Plonky 2 has a very good circuit for there, and optimizing this aggregation circuit is super important. Okay? There is a talk, I think in 1 hour or so, I think it's in this room, that will give more details on this optimization, parallelization, all the proofs that we have been running in a supercomputer and doing experiments, and see that all these numbers get very, very good, and this scales very well. Okay, future plans, a lot of things to do, a lot of things in the Verilog, a lot of optimizations that we want to implement, and you can try it. It's working. Right now we have a basic things working. The last time that I said that in a scenario, somebody created a Tornado Cache and was a little bit a nightmare. But just this is work in progress. Okay, so I would say at this point it's in the status that it's working. It requires some refactors of some pieces, some cleanups, some documentations, and we hope that, let's see if in the upcoming weeks everything looks nicer. And we want to build it has no precompiles. I mean, these state machines are limited, but you can build any program and you can prove any program. For these precompiles or for these specialized state machines, we take maybe 2-3 months still to complete. Okay, and that's very much my presentation. Enjoy it.
Thank you very much. Let's go through some questions. So what issues did you run into using RISC-V64 that RISC-V32 wouldn't have?
I mean, well, we have been checking what's better, what's worst. Here there are, there are pros and cons. I would say that the big pros is that when you are doing, especially when you are running in Rust, you are doing a lot of mem copies. I mean, you are moving a lot of memory information, and when you are using 64 bits, this is much, much, much more optimal. I would say this is one of the things that we saw, that there is a lot of copies in moving back and forth in a place, and because also the current systems are 64 bits, so everything is much more standard. For example, if you want to build, if you want to use Rust, is 32 bits is okay, but if you want to do Go, for example, you cannot do it in 32 bits, so you can do it in 64. So 64 is also much more standard. But again, the different tests that we did is that we're slightly better doing in 64 bits. So that's why we stick it at 64 bits.
And how will this be different than SP1 RISC-0? We still need to do some benchmarks and compare. But here the thing is that we are designing not for cost. I mean, that we are here. We are going to push as hard as we can in doing the speeds as fast as we can. So it's difficult to compare. It's difficult to compare yet. Also, we have some these machines, these special state machines that needs to be finalized. But the numbers that we have seen is that we are much faster, especially in CPU. We are working very much in the GPU, and the numbers are quite promising. But again, I don't like to talk yet about the numbers because it probably would not be fair, and things needs to be more settled. I would probably on both sides to start getting some real comparisons. From a developer experience point of view, what does the developer need to do to encode the chain rules into Cisc?
Just write the Rust code. I mean, just write a program that do the whatever rules that's in there. Just a side note here is take care on the security of that. When when you're getting some input and getting some output, the input you can still have soundness problems if you are not writing the right way. So you need to understand a little bit how the things work, even if you are writing a program in Rust, because there are some security issues that can happen there. But yeah, at the end is writing a Rust code.
And are there any drawbacks that come with Cisc?
I mentioned these security things but this is common in any VM. Okay, you still need to understand a little bit what's behind, but it's much more practical, and it's much easier to write a Rust code and audit a Rust code than not an assembly written in some specific special processor there.
Don't all these improvements by build specific hardware, are they better than making optimizations on VMs? I think that's what that says.
Maybe if they do, we will implement them. But they are not hard to build this hardware. I mean, this is not like real hardware that you need to build like machinery and yeah. This is just a program, and it's electronics. You need to have them the right way, and once you have it, they are already there.
I don't know what these mean, so maybe you could read them out if they make any sense to you.
Yeah, this is, I would probably need the context, but this is, at the end, is the position of the registers, because we are emulating registers in RISC-V, so we are setting specific positions in the memory that actually are the registers, and this is just defining the constants that defines the registers in there.
There a question in there?
Yeah. That's very much the thing. I mean, we can give you detail. I mean, there is on that, but that's the developer needs to write PIL2. Not at all. Not at all. Unless you want to build maybe some specific state machines. I mean, some coprocessors or things like that. That then you can extend that way. But the idea is that the final person that's writing in Rust is writing Rust, and that's it.
Great. Give a hand for Jordi Bailina. And we will be back after lunch to talk about client diversity with Daniel Lerner from Besu. Welcome back from lunch. I hope everybody ate. So next up, we're going to have from Besu, Daniel Lerner, talk about client diversity. Welcome, Daniel.
So hello everybody, my name is Daniel Lerner. I'm a Besu developer at Consensus, and I'm going to talk about the benefits of client diversity. So first of all, let's start with who here knows what client diversity is? Can you raise your hand if you know? Okay, I think almost everybody. So for the people that do not know, in Ethereum, to use Ethereum, we have different software programs. Especially since the merge, we need two pieces of software. We have the execution layer, which is basically the EVM, or whenever you call an RPC endpoint, normally like get balance, if call. And we have the consensus layer, which is the proof of stake part. And for each of those two pieces of software, we have a lot of different implementations. On the execution layer side, we have Geth, which is written in Go, Nethermind in .NET, Besu, which I'm working on in Java, Aragon in Go, Ref in Rust, and Ethereum just in TypeScript, and the same on the consensus layer. We have Prism, which is in Go, Lighthouse, Rust, Deku, Java. Nimbus is written in Nim, which is like a variant of C or C++, no, I'm not sure. We have Lodestar in TypeScript, and we have Grandine. In terms of distributions, on the execution layer side, historically, Geth is what we call a majority client. This means the majority of users are using it. On the consensus layer side, the distribution is more even, mainly because they have all started at the same time. They have all started more or less at the merge. So that's a bit better. So in the end, why are we doing this? So what are the benefits of doing the same piece of software several times? And I'm going to use this iceberg metaphor here, basically starting at the tip of the iceberg, which I think might be the most obvious answers to this, and then we are going down to the less obvious benefits. So the first one is stability. That's the very top. Here we have an example where Vitalik himself wrote on Reddit on the 24th of November 2016. There's a consensus flaw in Geth. We have identified the problem, and now we are in the process of testing a fix for a release. So basically what happened is there was just a bug in Geth. And at the time of writing this, there was already a second client, which was parity. And basically what happened is the two clients processed the same chain, and at some point, because of the bug, they forked off, and we had two chains. So after a while of debugging, they needed to find out, okay, which is the correct one, and basically fix it. So what happened here is that even though Geth, which was at the time the majority client, had a bug. The chain never went down because parity was still there, basically to continue in the meantime. Parity continued the correct fork, and once Geth was fixed, Geth rejoined this fork. So here is basically, I think, maybe the most obvious one. If you write software more than once, every piece of software can have a bug, but that two versions of the same protocol have exactly the same bug is rather unlikely. So we can basically make sure that one of the versions will work normally one at a time. Then the other thing is correctness and error detection. How do we even know that something in the protocol is wrong? So I mean, there are very obvious errors in software. That's normally when the software is crashing. But what if the software just has a bug and it calculates something incorrectly? Here we have an example from the 15th of August 2010, long before Ethereum has existed. This is the Bitcoin Talk forum. There is a user that says, the value out in this block is quite strange. And then here at the bottom it says 92,233,720,368 Bitcoin. Basically what happened is there was a bug in the Bitcoin software and somebody triggered the bug, we don't know if it was on purpose or not, twice, and created 180 billion Bitcoin. Even for people that do not know a lot of Bitcoin, they most probably know that there is a very hard limit of 21 million Bitcoin. So 180 billion obviously is way too much. And why I chose this example is Bitcoin traditionally chooses only to run one client normally. What happened here is that this client had just a bug. It produced, in this case, too much Bitcoin, but the chain still continued to run. There was nothing obviously wrong with the chain, just that this one user was really looking at the transaction, was looking at the output, and that's how the error was detected in the first place. This, in the example before from Ethereum, was very different. In Ethereum, two pieces of the same software ran, and then we could see that they diverge. So it was very, very obvious that something is wrong. Here, it was really by luck that somebody checked this. And then at the end, at this time, Satoshi was still around. They fixed the bug, basically rolled the chain back. There were like 50 blocks afterwards produced. They were afterwards invalid. And then they had a valid chain again. Then the next point is not just avoiding errors, but especially avoiding catastrophic errors. Here, 6 months before the merge, Dankrad Feist, one of the Ethereum Foundation researchers, wrote an article that says, Ethereum merge, run the majority client at your own peril. So why did he write this? Before, in proof of work, in the first example that we saw, when one of the clients had a bug, it in the end produced an invalid fork, but you could always go back. With the merge and with the change to proof of stake, we have a new concept which is called finalization. Finalization means at some point, normally after what we call 2 epochs, which is around 12.8 minutes, the chain finalizes if it has more than 2/3 of the votes, and you cannot go back anymore. This is a very, very nice property because you know for sure if your transaction was in a block that has finalized, it will never revert again. But there is one problem with this. I don't want to go into too much details because it's basically not the goal of this talk. But in the finalization process, if a client, a majority client who has more than 2/3 of the nodes or of the stake has a bug, it will produce the invalid chain A. And it will attest, which is basically vote, for the 2 blocks. These are the two red arrows. Even if the bug is detected because we have other clients who will let us know that, and the bug is fixed, all the clients that were on chain A cannot go back to chain B anymore. Because in order to do that, they would need to vote here for what is marked as the X. And this is not allowed by the protocol, because they basically jump over one of their own votes. And this is what we call a slashable offense. A slashable offense means the validator does something that can cause the chain to not find consensus. So we are not sure which of the 2 chains is correct, and this is what could happen here. Okay, so this was a very, very serious problem, and Dankrod wrote this like half a year before the merge. So the most logical outcome most probably would be that people would be aware of this, and people and validators would make sure that no client had more than 2/3. At least that's what we thought. The reality looked very, very different. So this is the client distribution from beginning of this year, and Geth had around 84% of the stake of all the nodes. So this means we had a ticking time bomb for 1.5 years, where basically one consensus bug in Geth would have triggered the outcome before. And if this would have happened, we would have destroyed billions of dollars of value in ETH in order to revert to the correct chain. Okay, so now we had this ticking time bomb. What should people do? I'm one of the developers of a minority client, so we tried our best to make our software competitive. But then, unfortunately, Murphy's Law hit, and we had in Besu on the 6th of January a bug that basically took the node down. And the second one is from Nethermind, which is the number 2, which was 2 weeks after. So within 2 weeks, the number 2 and the number 3 client had a problem. So we had now the issue that Geth had already this huge majority, plus we had 2 problems. Surprisingly, those 2 events led to the outcome that people finally were talking about the problem with the finalization of a supermajority client. Here, a big shout out to the ETH Staker community, to Nixo, to Yorick Down. They really educated people about this problem, and stakers and validators finally realized, okay, that's a huge issue, we need to do something. And that's why right now it looks like this. So Geth has gone down from 84 to 52, so it's below the 2/3. The issue, basically this was outlined before, it cannot happen anymore. Besu and Nethermind have both increased a lot, so now the situation looks much better. But what this also means is client diversity is a choice. The community has to choose it. If not, even though we have several implementations of the same software, it will not happen. Here is one example where this does not work. If people are thinking about Bitcoin, they must probably just think about one client. In reality, Bitcoin has 14 different clients. Some of them just on mobile, because Bitcoin is more light client friendly. Others are full nodes. But despite that, 98.63% of all the nodes are running Bitcoin Core. So even though a lot of clients would be available, the Bitcoin community chooses to run only one, which basically means they do not get the benefits from client diversity that they actually could have very easily. Then here's another point that's maybe already a bit more hidden, is to make the specification of the protocol easily accessible. When several teams across the globe work on the same piece of software, you are basically forced to first start with a specification. You're basically forced to first write down, okay, what actually are we going to do it? And we have several resources in Ethereum for that. We have the Ethereum Magicians Forum, which basically normally is where discussions are starting about changes. We have the EIP process, which is then the actual spec of the changes. We have the Ethereum execution spec tests on the execution side, which basically means all the changes that we are doing and all the protocol rules are available really as tests that you can run. So all the clients can run the same tests, and this is very clearly defined what is the expected behavior. Another thing that we have that is less blind spots. With client diversity, you will never have no blind spots, but at least you can reduce your blind spots. What I mean with this is when we look where core developers are located, we have a big number in North America, big number in Europe, and a big number in Australia. This means geographically, more or less, the distribution is not so bad. But we have, for example, right now, no team in Asia, no team in Africa, no team in South America. If people were yesterday at Justin Drake's talk about the Beam chain, at least the situation should improve for Latin America and for Asia, and we will have 2 new teams. And basically the goal is that they can bring their own view, their own life experience into the process, and they can help us reduce our blind spots, which developers from the Western world maybe do not see. So for example, people who use stablecoins in Latin America or Asia, I think most core devs right now are not in situations where they would really need this. Then when you have different clients, those clients can do different improvement and experiments. Here I have just for every execution client one. There are a lot of them, but we can quickly go over that. Nethermind has, for example, done a lot of performance work recently. They have reached 1 gigagas, which is like our goal for layer 2s. In Besu, we have parallel transaction processing. So right now on Ethereum mainnet, you can do parallel transaction processing without problems, which is also something that was long ago also for L2s. Aragon has worked very hard to make archive nodes run on consumer hardware. Especially the disk requirement went down from like 16 terabyte to 3 or 4. Ref has introduced execution extensions, which basically allow you to modify the client without forking it. And another example is EOF. If you don't know much about EOF, if you're a smart contractor, you will like it because it basically gets rid of the stack to deep errors. And it finally allows us to safely increase the smart contract size limit eventually. And this is mainly driven by the minority clients. And then if you think, okay, I'm running a majority client, what benefit do I have? The benefit is that the majority client eventually can copy the features. For example, here, this is Peter, the team lead of the Go Ethereum of the Geth team, tweeting out that they will, the XX, the execution extension support from Ref, will also do it to Geth. So because one of the minority clients introduced it, finally the majority client gets it as well. Here is another slide, which is a bit more abstract, but you have a lower risk of protocol capture or failure. if you have just one team, there are different types of attacks a government could do. They maybe cannot attack the protocol, but they could infiltrate the team, or they can pressure somehow the team to push a change that they like. A team can withhold updates, something that the community maybe really wants. The team cannot force the community to run a specific software, but the team can say, okay, this one update, we do not like it, we will not ship it. And then the community will have a very hard time to get it. And simply, if you have one team, they can just eventually abandon the client. So then, again, you have a problem. And then we go to the last point, which is in the end, permissionless contributions to the protocol. This is very abstract, but in the end, what this means, if you have client diversity, it means everybody can become a core dev, including everybody here in the room. So if somebody is interested in this, here in the slide, we have the different repositories of the clients. This is if you are interested in programming. There are also another things, if you want to just keep up with the protocol. On Twitter, you can follow Tim Baker or Christine Kim. They always share updates. You can join the Discord server. You can look at the EPS. There are a lot of things to do. So that's basically it. So thank you for your attention.
And we will go through questions. If fork A never finalized, a validator that voted in fork A can later attest in fork B when the fix is released. Can they do that without getting slashed?
Yes. So this means if the majority client has less than 2/3, that is possible. Yes. So the main thing is really no client should have more than 2/3 of the staking votes.
So we have some more time for questions. We have more questions in the queue. Does anybody want to ask a live question? We have one over here.
Ah, there is one.
Oh, how do you get the numbers on different clients running different running nodes?
Yeah. Okay. So that's a good question. So in the end, we have no reliable way of doing that. People do some sort of fingerprinting where they analyze different blocks that are proposed, and then they can basically estimate which CL clients they are. For the execution clients, we do not have that. There were recently proposals. We have like one field when you propose a block where people can basically write random data. There are proposals to basically write in which EL and which CL you run. And then we have better estimations. But the numbers that I showed before, they mainly rely on self-reporting. So the big staking providers in the end report the numbers, and then there is like a huge chunk of, I don't know, 1/3 of the network we do not know. But for the worst case assumption, we just say it's the majority client. And still with this worst case assumption, no client has more than 2/3. But yeah, we do not have exact numbers. We only have approximation of the numbers.
Thank you. Could you steelman the argument that Bitcoin puts forward for having one client and why it's wrong?
Yeah. So one client, in the end, means there is less politics involved, maybe in discussing changes. So in Ethereum's case, you basically have to convince different teams that they want to change. Although Bitcoin is quite resistant to change by itself. The other approach, I don't know. I mean, is like what I mentioned before with the capturing of a team. But yeah, so for me, it's actually hard to steelman this. You just avoid maybe, I don't know, certain errors by using more than 2 clients. But yeah, as I said, for me, the benefits far outweigh the downsides of having just 1 client.
Any more live questions? Great. Can we give a hand to Daniel for his talk?
Thank you.
And in 7 minutes, we'll have a talk from an Aragon client dev. Alrighty. Our next speaker is a core developer at the Aragon execution layer client, and he is here to tell you about the newest version of the client. Please welcome Mark Holt.
Where do we go? Okay, hold on a sec. I'll get the slides in the right place. Yeah, hi, I'm Mark Holt. I work on the Aragon team. And basically what I'm going to talk about today is Aragon 3, which is the kind of latest incarnation of Aragon, which is just coming out of alpha. So we're expecting by the time we get to Petra to have that as the client we would like everybody to use. So the purpose of this talk is to talk about Aragon and what it's doing and why it's slightly different from other clients. And what do I... Oh. So yeah, so Aragon, a bit about us. Aragon is a client team. Now, although we're principally used for execution, in fact, one of the things about later versions of Aragon 2 and Aragon 3 is actually it's a combined client. It basically does both CL and EL in one application. Now, it's based on a TurboGeth, which was a project which I'll talk a little bit about. But it's essentially built to become mainly used as an archive client, which is, you see, we're down at 2% of usage. And that's because basically we get used for people who've got an interest in the whole history, essentially. And historically, we've not been quite so good at operating for people who are purely doing validators or are interested in the tip of the chain. Now, hopefully with Aragon 3, that will change a bit. So what I'm going to talk about today is just an overview of what Aragon 3 is, the journey we've been through from TurboGeth, which is where we started from, to where we are now. I'll explain a little bit about the architecture of Aragon 3, because I think it's important in understanding how we think it's different from other clients and what the implications of that are. And then I'll talk a little bit about the future of what we've got. So I called this talk Aragon 3, a paradigm shift for clients. And that's partly because I think within the Aragon team itself, we think about the client slightly different from other clients at the moment, especially in, I guess, the Ethereum space, in that we don't really think about consensus versus execution because we've got a combined client. What we think more about is what happens at the tip of the chain and effectively what happens after that, because a lot of the technical work we've done is about the transition of data as it goes through the life cycle from coming out of a mempool to getting into consensus, and then what happens with all of the data afterwards as it gets into the into the archive space. Because I mean, for us, we never throw data away, and that includes both CL and EL data. So we're basically working out how do we store and distribute this stuff. So we've kind of got a model that has an application that thinks about chain dissemination, which is the live chain and what happens when it operates in real time and how do we work that effectively. And then there's a whole process of, once you've basically got the chain data, how do you then distribute it efficiently to other nodes? And we kind of split that, and we don't necessarily do that through the entire, the same life cycle as everybody else. So I'll talk a bit to start off with about the Aragon journey, because I think it's interesting. It's also interesting in terms of the last conversation we had, which was about client diversity. I think one of the interesting things about client diversity in the context of Aragon is it's not just for the live chain. I mean, one of the things about client diversity is Aragon's had quite a long journey to get from where it started from to where it's ended up now. And that's effectively been funded out of the community because it accepted that there wasn't a one-size-fits-all. And because there's not a one-size-fits-all, if you believe enough about something, you'll get the backing to keep going, although there are several other people doing the same thing. And that can lead to different outcomes. So if we talk about where do we start from? So I think Alexei, who's actually in the audience here, was talking in Devcon 4, which is and introduced TurboGeth, which was a change to the way Geth stores data. So that was in, Devcon 4. We're now several iterations through the journey, and we've probably finally come to the point where we're delivering on the original vision. And I think that's another thing about the space that we're in, is that actually, if you look at Aragon, it's had the space to kind of learn over 7 or 8 years to get to a point where it's actually delivering a product without the kind of pressure of you got to get time to market. And if you failed within the first couple of years, you've got to go off and do something else. So there's longevity in this process. Now, I think if you look in TurboGeth, that what it was doing was looking at the data storage and saying, if we have a look at the way data is stored in and do analysis of it in the clients, we can do better with a storage model, effectively. And I think the TurboGeth piece of the journey was about essentially how do we make storage more optimal. And if you look at the numbers, the lesson there was you look at the majority client, and we with the analysis that we did and the work, we got down to a fifth of the storage model. So you get to a situation where the effort was worth it to get something slightly different, essentially. Now, I think what that does is says, right, there's a product here, and people start using it because there's a benefit for people because it's an important process. So that's what got the whole thing kicked off. And then essentially what we ended up with there is an ongoing development of Aragon, which took that original idea and Des pushed it to its next conclusion. And the next stage of this journey was the realization that actually, if you start caring about the data and the data going into a database, you start thinking about what the database is and asking yourself the question, can you optimize that? And the other thing, Des pushed it to its next conclusion. And the next stage of this journey was the realization that actually, if you start caring about the data and the data going into a database, you start thinking about what the database is doing and asking yourself the question, can you optimize that? Des pushed it to its next conclusion. And the next stage of this journey was the realization that actually, if you start caring about the data and the data going into a database, you start thinking about what the database is doing and asking yourself the question, can you optimize that? Des pushed it to its next conclusion. And the next stage of this journey was the realization that actually, if you start caring about the data and the data going into a database, you start thinking about what the database is doing and asking yourself the question, can you optimize that? Des pushed it to its next conclusion. And the next stage of this journey was the realization that actually, if you start caring about the data and the data going into a database, you start thinking about what the database is doing and asking yourself the question, can you optimize? Des pushed it to its next conclusion. And the next stage of this journey was the realization that actually, if you start caring about the data and the data going into a database, you start thinking about what the database is doing and asking yourself the question, can you optimize that? Des pushed it to its next conclusion. And the next stage of this journey was the realization that actually, if you start caring about the data and the data going into a database, you start thinking about what the database is doing and asking yourself the question, can you optimize that? Where we've ended up. So more about how that works by giving you a bit of the way that the Aragon architecture works, so you can see what we're actually doing inside of the model. So essentially, a lot of what Aragon does and a lot of what the team work on is this kind of process where we think of the model. So essentially, a lot of what Aragon does and a lot of what the team work on is this kind of process where the model. So essentially, a lot of what Aragon does and a lot of what the team work on is this kind of process where the model. So essentially a lot of what Aragon does and a lot of what the team work on is this kind of process where the model. So essentially a lot of what Aragon does and a lot of what the team work on is this kind of process where the model. So essentially a lot of what Aragon does and a lot of what the team work on is this kind of process where we think the model. So essentially a lot of what Aragon does and a lot of what the team work on is this kind of process where the model. So essentially a lot of what Aragon does and a lot of what the team work on is this kind of process where we think about essentially distributing a verifiable binary version of the chain from one machine to another, essentially. And what this diagram is showing is you've got a set of pages and they're all hash verified. Now, what are the implications of all that process? Well, they're basically what you end up with is very quick sync performance, effectively. So the big difference between Aragon 2 and Aragon 3 is the amount of time it takes to sync something. And this is, you see this particularly on large chains. So basically, my role in the Aragon team, I'm mainly working on Polygon rather than Ethereum, page cache, effectively operating the chain. And I think that with that, I'm out of time and I'm done. Thank you.
So two of these questions I'm going to combine, which is how do you compare in terms of speed and cost efficiency and storage compared to the other execution layer clients?
Depends which client. So something like, so I think we're probably still, and don't quote me, we're about a fifth of the storage for Geth on a reasonable size chain. The others I'm actually not quite sure about.
Are there other pros and cons of running Aragon versus any other execution layer clients?
Yeah, so Aragon is good in storage performance and its RPC layer. It's not so good if you're doing things like validation, because we simply haven't worked on that as a, we've optimized the storage, not the interactions. But I think that is less true with Aragon 3, effectively.
Great, thank you. How much bandwidth overhead does Aragon introduce to push verified data across the network?
As much as you want to give it. So basically what you can do when you run an Aragon node is you can tell it how much bandwidth it wants to give away. And it basically, if you don't want to have that turned on, it doesn't take any overhead. If you're conversely a seeding node, it'll run as much bandwidth as you want to give it, basically.
We've got a lot of questions coming in at the last hour. Is Aragon 3 going to make the support of other EVMs more easily? What about L2s?
Yeah, I think it is. I mean, one of the things that we're explicitly doing with Aragon is doing L2 support. I think the big difference for us in 2025 from 2024 is we'll spend a lot more resources in actually actively working with L2 chains to get an L2 version of Aragon. And one of the reasons for we work with more chains, we're simply building components. Because what we want to componentization is so that we can have a core Aragon that does the database thing, and then as we work with more chains, the componentization is so that we can have a core Aragon that does the database thing, and then as we work with more componentization is so that we can have a core Aragon that does the database thing, and then as we work with more
blockchain test can not only have individual transactions, but also contain blocks, and these blocks can contain one or more transactions. So they test slightly different things, or concentrate on different things. So state tests can test opcodes or gas usage, and a main part of our work is really to verify smart contract interactions. And we can verify that transactions that should get rejected do get rejected. And blockchain tests validate block progression from block to block rejections, and fork transitions. So before we go to the new, let's have a look at the status quo at the merge and see what the state of things were for testing at the EL back when we met in Bogota in Devcon 6. So since Frontier, there's the repository that's managed test generation, or the body of tests, is Ethereum tests. And this is a huge corpus of tests, mainly curated by Dimitri, who's sitting right over there, who created an amazing body of tests, later joined by Ori. And you can see that there's almost 5,000 tests for Cancun. And these test cases are written in YAML, and typically by hand. And they contain comments as well about what the test does. And then they get generated by a tool in another repository called retest.eth, which generates JSON test fixtures using a reference EVM implementation. So the test fixtures are then, so this process is called filling the tests, and the reason is that the test fixtures contain much more information about the test, in particular all the changes in the post in the state, and importantly the state root, which is basically the fingerprint of a change that you can really verify that every client did exactly the same. So in 2021, Ori had the idea to create more complicated tests, and so instead of just writing these YAML files by hand, he started generating many YAML files using a node script, like using JavaScript. And this allowed him to create many test cases by looping over opcodes, for example. So we get to programmatic tests and generating tests programmatically. So around the same time, in 2021, Light Client was at one of the first interop meetings in Greece and was working on account abstraction and wondering how can we test that. There's so many parameters that we need to change and so many test cases that we need to write. How can we possibly manage this complexity by writing YAML files? And he also came to the same conclusion that we should have programmatic test generation. So what Light Client did was he sat down after the interop and wrote a testing framework in a repository called Testing Tools, which specified the tests as Python and then generated JSON from the Python. And so this makes it easier to define new test cases and parameterize test cases. So he worked on this for about 2 months, and then this repository kind of went into hibernation and didn't see much work on it, or actually no work until Devcon 6. So at Devcon 6, everyone was ecstatic that the merge had gone so well, and it was very forward-looking that people were seeing how we're going to handle testing all these complicated features that are coming into the EVM in the upcoming hard forks. And so there was a discussion about what kind of framework can we use, or what should we write in order to handle this. And Light Client piped up and said, I think I've got a project that could be useful. And so this became Ethereum Execution Spec Tests, which is the repository that I work on today. So Mario, who was a protocol tester at the time, sat down and started writing the first test cases, building out the test framework a little bit broader, and was then soon joined by Spencer in January of 2023. And they wrote tests for all the EIPs included in the Shanghai hard fork. And in the first release for Shanghai, or the final release before the fork, you can say, they had 194 test cases to handle the new features coming into Shanghai. So Shanghai really showed us how powerful a programmatic test framework can be, and how easy it is to write test cases in Python. At that time, the repository used completely custom code to collect all the test cases and generate the test JSON. And although we're not writing tests like unit tests, we had the idea, what if we just use a standard test framework to do the job for us? And so we rewrote the framework to use PyTest, which is like the de facto test framework for Python. And PyTest has a lot of advantages. It's extendable via plugins, and there's a large existing ecosystem for plugins. So if we ever need a new test result format, we can just install a new plugin and get the test results in JSON or in XML or in HTML. You can also add your own custom plugins, which is very important to us because that's basically how we've implemented all our commands within East in order to generate tests, and later we'll see execute them. It allows for easier debugging, and last but not least, it means that we can really easily parameterize test cases. And as you can see in the screenshot, which is from our documentation, how heavily we parameterized blob transactions, for example. So what you're looking at is test valid blob transaction combinations. And so this is a blockchain test that has 1 to 6 transactions, and each transaction contains a different number of blobs, and we test all possible combinations that are accepted by clients. And we have an accompanying test for invalid blob transaction as well. And so essentially, to parameterize this test becomes one-liner, and if the spec would change and the max blob count increases, we can change it in one place and generate many more nice tests. So this has really accelerated test development, and you can see that in the Cancun release, we had over 2,400 tests included in that just for Cancun. So this has also really helped us to create a contributor-first repository. We really want, this should not be a dark corner of protocol development. We really want EIP authors, EIP implementers, even white hat hackers, anyone to come along and use this repository. We want them to come and write tests. There's soon going to be a new tool to help you get started interactively, thanks to Rahul, who was an EPF fellow. And we'd also like people to be able to generate tests from a transaction hash of a bad transaction on a DevNet, for example, automatically. So you generate the Python code directly. And we also want people that, even if they're not directly contributing to the repository, EIP implementers, after they've been working on their implementation and wondering if corner cases are covered in the test cases, they can come to our repository and look at our documentation, browse it, and really check whether the coverage is there that they expect. Is the corner case they just thought of, is it already in the tests, or should they come and pester us to make it, or even add it themselves? This has really helped us unlock parallel development for multiple forks in parallel. And for Prague, we've got 2,500 test cases, and in parallel, we've been also implementing tests for the upcoming fork for the EVM object format, where we added a new test format to validate EOF bytecode. And we have 9,000 new test cases already for EOF. And this is really a huge thanks to the Ypsilon team and to Dano, who have done an amazing job of writing these tests and contributing to our repository. Also, a big thanks to Ignacio and Guillaume and Spencer from the testing team, who have contributed to adding the infrastructure to the framework in order to test Verkle. So it's already possible now to fill and run existing tests until Shanghai for the Verkle transition. And the witness has already been added to the fixture format, so we're ready to test that when we move closer to Verkle. So at this point, we had a relatively usable filling framework for generating these tests. But we really missed something. We really missed the feedback. So if you want to really test a client, you can't just fill the tests. That's just generating the tests. And we mentioned before that we use an EVM reference implementation to fill out the features so we can get a state root that we can compare to other implementations. This is a differential test. And if you want to really test a client, you've then got to take this JSON and then test the client by getting this other client to consume the JSON that the first client produced. So it's a two-step process. And we were missing fast feedback within our repository. So we then added 3 commands for us as test developers to quickly run the tests against a client. The first one, consume direct, you can execute or run the test against the client's native consumer, and the last 2, consume RLP and consume engine, allow you to test a client in the Hive test environment using different code paths, either by loading RLP encoded blocks upon startup or via engine new payload. These commands that were in thanks to the modular architecture we've created using PyTest plugins. And we really use combinations of these plugins in order to achieve the commands that, or the tooling that we need in the repository. And Mario came up with an excellent idea that to extend the framework to allow execution of these tests on live networks. So he added the executor command, which allows us to attack live DevNets, which we just did in the framework, in the workshop a couple of hours ago. So the execute command doesn't generate JSON fixtures. It takes the test cases, generates a transaction, and executes it against a client using its RPC endpoint. This really unlocks a totally new use case for our tests and really allows us to get out of the staging-like setting that we've been executing these tests in until today and run them in a more production-like setting. So we can really run these tests against DevNets. So we've done a lot of work over the last year or 2 years to improve the lives of test implementers. But we're not done yet. We'd really like to also help improve the lives of client developers. One large job, but still not done, is we'd like to merge the corpus of tests from Ethereum tests into East. And we'd also like to, this would mean that clients can then, they only need to download 1 artifact. Because Ethereum tests are still, they're still very important to consume. And at the moment, client teams have to develop, to consume tests from 2 different sources. And once we manage to merge these tests, we can catalog them a little bit better, and clients only have to depend on 1 artifact to test their clients. And as you can see, we've developed quite a lot of tooling over the last couple of years, and we'd like to be able to provide this tooling to client teams so they can use it in their test flows in order to get faster feedback on their performance on a PR basis, so they can rapidly iterate on the development. For that, we also would help if we had faster test execution. Hive is quite slow, for example, because this test environment is a system test which instantiates a client in a Docker, and this client gets, the Docker container gets pulled down and started up for every test. We'd like to make this a bit faster so clients can get faster feedback. Additionally, we'd like to enable easier test debugging so that clients can really run the same test, hopefully, if possible, in their native environment, so they can drop into their debugger when they need to in order to find out what the problem is when they're running the test. We also would like to improve the development cycle. So our team has recently, the East team has recently merged with the execution specs team, the EELS team, that handles the Python implementation of Ethereum specs. We've merged with them to become one team called Steel, the specs and testing of the Ethereum execution layer. And we now fill all our tests. The reference implementation for filling tests should really be EELS. And it is for all forks, up until including Prague and soon Prague. This would unlock a kind of test-driven development. It's a rather coarse test-driven development because you need an end-to-end test, obviously, for your client. but it does mean that when a client implementer comes to implement his code for the EIP, he will have tests ready to go, and he'll be able to check whether it's there. So the feedback will be fast, instead of having to implement it and perhaps wait for tests to arrive from another client. Another thing that we'd really like to add would be EIP versioning. So there's many different places where an EIP is defined or implemented. There's the Ethereum EIPs repository, there's the tests, and then there's all the client versions and the specs, of course. So there's multiple versions where the EIPs are defined, and if we can track the versions across all these components more easily, we'll be able to make a statement about whether these components are even compatible before we run tests, sorry. So we can even just basically exfail the tests, and we know that we expect a failure, and we don't have to try and debug something that doesn't make sense because the specs are just incompatible. And last but not least, we'd like to improve coverage. It would be amazing to be able to hook a fuzzer into the tests. So we already have a whole bunch of edge cases for EIPs, and if you could define which parameter you'd like to fuzz for these edge cases, it would allow us to run these via execute and get more test coverage. And we'd like to improve our documentation even more and encourage people to come and look at our test cases and try and contribute to new ideas to increase coverage. So I hope you see that the title of the talk is not just a meme. Our repository does protect by allowing clients to consume the tests, but now we can also attack clients on DevNets. So thank you very much. One of the main messages of the talk is really that we're here, and any client anyone who's interested in testing on Ethereum can reach out to us, and you can find all our contact details in our user document or in our repo documentation. Just go to the docs that you'll find linked in the repo. Go to Getting Started and Getting Help. All right, thank you very much.
Let's take some questions, starting with the most upvoted. Can you programmatically check test coverage?
That's an excellent question, and Dimitri's been working very hard on this. And we now have a GitHub action that actually does exactly this. So it detects if a test has changed, and then it will basically fill the test before and after, and run the fixtures against EVM1 from the Ypsilon team, and get a test coverage on EVM1 before and after, and then literally check what's the line difference in coverage. So yes.
Were significant bugs found using this testing framework?
I mean, we hope to catch the bugs earlier, right? So we don't want to catch the bugs on DevNet, really. We want to catch the bugs as soon as possible while the client is implementing. And so yes, but hopefully you'll never hear about it.
Up until Pectra, which EIP was the most challenging to test?
Up until, not including Pectra?
Not including Pectra.
Let me think. I would say probably 4.844. Yeah.
Are test fixtures in Ethereum spec tests already included in Ethereum tests?
Yes, but we'd rather go the other way. So we consider the future of testing Ethereum spec tests, and so we'd rather get Ethereum tests in execution spec tests. As an interim solution, Dimitri filled our fixtures from retest ETH using our framework and included them in retest ETH, in Ethereum tests, like the test repository. But because our tooling is in our repository and we can generate releases more quickly, I would prefer to keep our releases in execution spec tests, and I think that's the approach we're going for now. And hopefully soon, before EOF, we'll have Ethereum tests and execution spec tests.
Can you give some insights into the testing limitations? Like what is not easy to test?
I mean, definitely one of the challenges is keeping up with specs. So it's not easy to test a moving target, which is maybe not the answer you expect, but it's definitely very hard to keep up with the pace of Ethereum development and have tests ready for clients to go.
Is the reference EVM independent of other clients?
Yes. And I'll just say again, the reference EVM.
What does filling from eels mean?
Filling from eels means that we have a test case, which may just be a few lines of code. That describes the entire test case, thanks to the framework, and eels. And eels basically, so the way it's done is there's a tool called the transition tool, otherwise known as T8N. And this gives a doorway to the EVM, and we give it inputs and a transaction, and this EVM, the T8N tool, gives us the expected output. And so this means that we generate a lot more information. As an example, the test framework can't tell you what the balance, like we could add it, but we don't tell you what the balance of an account is after it's sent to a network, because we don't know all that, we could add all the gas costs, but there's a lot of complicated things that we need to track, and we don't track all of them. So if we wanted to track all of them, the test framework can't tell you what the balance, like we could add it, but we don't tell you what the balance of an account is after it's sent transactions to a network, because we don't know all that, we could add all the gas costs, but there's a lot of complicated things that we need to track, and we don't track all of them. So if we wanted to track all of them, we'd be implementing an EVM, and we don't want to do that. It's not our focus. So we use a reference in EVM, eels, that gives us all this information, including the state root.
Will the engine API get incorporated into this version testing mechanism?
It is partially, because we generate different test formats, and one of the test formats is called the blockchain engine test format, and these fixtures can be sent to a fully instantiated client that's running within a Hive environment, and they're executed using engine new payload. But the engine API specifically, this is really about more EVM specs rather than engine API specs. There's a separate simulator in the Hive repository that handles these tests.
Great, thank you so much. We are out of time for questions, but if you have one of these questions, find Dan afterwards, and we will be back in 5 minutes.
Because we generate different test formats, and one of the test formats is called the blockchain engine test format, and these fixtures can be sent to a fully instantiated client that's running within a Hive environment, and they're executed using engine new payload. But the engine API specifically, this is really about more EVM specs rather than engine API specs. There's a separate simulator in the Hive repository that handles these tests.
Great, thank you so much. We are out of time for questions, but if you have one of these questions, find Dan afterwards, and we will be back in 5 minutes.
This is really about more EVM specs rather than engine API specs. There's a separate simulator in the Hive repository that handles these tests.
Great, thank you so much. We are out of time for questions, but if you have one of these questions, find Dan afterwards, and we will be back in 5 minutes. Out of time for questions, but if you have one of these questions, find Dan afterwards, and we will be back in 5 minutes. Out of time for questions, but if you have one of these questions, find Dan afterwards, and we will be back in 5 minutes.
Welcome to the afternoon session, everyone. I'm Ahmed. I'll be your MC. So our next speaker is going to be talking about using REST execution extensions for next generation indexing. Please give it up for Alexei from Ithaca.
Hey everyone, I'm Alexei. I work on Reth at Ithaca. And today I'll be talking about Reth execution extensions for next generation indexing. So let's start with what is indexing. Why do we need it? Ethereum is a database in itself. It has history, state, and receipts. And it sounds like it's sufficient for all our needs, but it's not, because history is too large. And as an example, when you want to query all the transactions for a user, you need to go through all the transactions in the history. Same with state. You can query the account balance and account nonce very easily. But for example, to query the ERC20 balance, you need to actually index every smart contract for the ERC20 and calculate how many tokens does the user have. Receipts and logs are good, they work, but unfortunately sometimes they lack all the required data in them. And you still need to know what receipts to query. So you can have some transactions that emit the logs about the deposit, for example, into the Beacon chain deposit contract, but you need to query the transactions for this contract. So people usually build indexers. Indexers are third-party solutions that store the data elsewhere. For example, it's Etherscan that we all use, it's Dora, and also wallets. Wallets are indexers. They usually outsource it to someone else, like Infura, Etherscan, whatever API. But to show the token balances, you also need it. And if you think about it, a rollup can also be a kind of an indexer, because you need to keep track of the deposits from L1 to L2. You need to derive the data from L1 to get the L2 state. For example, when syncing. So yeah, it's an out-of-node infrastructure that indexes on-chain data to get some useful data off-chain. So how do indexers work today? You, as an indexer developer, have several choices, and the most obvious one is using the JSON RPC. JSON RPC has the ETH subscribe method that allows you to get notifications for new blocks that arrive. This will get you the transactions, and you can also trace these transactions later. You can inject your code into the node source code. For example, you can have Geth or Reth or Nethermind code. You fork it, you inject your code for storing the data from the transaction into your storage of choice, Postgres, Kafka, whatever, and you process it later. And you can build on top of the existing node components and create your own indexing node that runs in the same binary, in the same process as the node itself. So let's go through all of them and talk about pros and cons. JSON RPC subscriptions, very easy. Every node has it. This is the thing that's almost spec'd. So people expect the behavior from every node to be the same. The cons of this approach is the poor performance, mostly due to JSON RPC serialization and data transfer, because you need to serialize to JSON, you need to make an HTTP request, then you need to deserialize all the things. It's difficult to handle the chain reorgs, because when your chain reorgs, you get a notification on the ETH subscribed WebSocket connection. But this notification doesn't tell you a lot about what was reverted and what was committed now. You need to figure it out by your own. And also, it requires the ad hoc solution, some like Rust, Python, JavaScript code that runs alongside your node, listens to this JSON RPC method, and stores this data somewhere. Okay, we have like a better idea. We can inject our code into the node source. We solve the problem with overhead on serialization and the data transfer. You basically do not leave the memory that the node uses, and all data is potentially accessible. So you have the access to the database, to the transaction pool, to everything that the node has access to. And Geth has it today. It's called light tracing, and as you can tell, it's very easy. You add your own .go file to some directory, you run Geth as normally, and it produces your logs. The cons of this approach are maintaining the fork of an original repository. So you need to fork get, you need to add a .go file into some directory. But if, for example, get introduces some new feature, you need to pull the changes, you need to resolve the conflicts, and then you can start running your node again. And the con is also that you are tied to the programming language that you use, that the node is written in. So in case of get, it's Go. So we have our own answer to that, and it's execution extensions. So let's talk about what are they. Extensions require allow you to consume a rework-aware stream of notifications coming from the node. Basically, you get access to all node components, same as in the approach with get. You get access to EVM database, transaction pool, payload builder. You use shared memory for communication. So the node sends a notification about chain commit. It has one block. This block is in memory, and all X-axis, for example, you can have 5 execution extensions. They share the same memory, so there is no copying going on. And it's also compiled into the same binary as Reth, and it's run in the same process. So as I said, there is no forking. I didn't say this. There is no forking because we use Reth as a library. That's the main, I think, difference that we try to talk about more. That Reth is an SDK, not just a node, and you can import Reth. You can use it in your own small project. 100 lines of code, 1,000 lines of code, doesn't matter. And when Reth updates, you just do cargo update, and it updates your dependencies. You also have the access to all the node components, as I said, and what's also very cool that you get access to the state diffs right from the EVM execution. So the EVM finished executing the block, it produced some state diffs and try diffs, and you can consume them. The issue is that you are tied to the programming language of Reth, which is Rust, which is not bad. So as I said, you can do whatever you want as like an indexer. You can do an indexer, a rollup, for example, a base rollup, an AVS, or an Oracle. And you use the power of the node builder in the Reth SDK to introduce a new RPC method for this indexer that serves your data to extend the payload builder, or add a new CLI argument to somehow configure your indexer without modifying the source code. This is an example of an XX. What happens here is that you consume the stream of notifications. There is 3 variants for the enum, chain committed, chain reorged, and chain reverted. And as you can see in the reorg, we have old and new chain. So you can undo all the state diffs from the old chain and apply all the state diffs from the new chain. And then the node is started in the fn main entry point function, which is like 10 lines of code. And it runs the full Reth node, just as a normal Reth node, but with your extension that node sends data to. So people today are already building stuff with X-axis. We have Tycho experimenting with the base rollup built on X-axis. We have Kona, which is an OP Labs project for derivation of L2 blocks from the L1, and it's also an XX. We have Shadow working on Shadow logs when you want to have additional logs in your app that are not in the source code of the contract itself. And you, on every new transaction with this contract, you modify the VM execution of it. And VFVM also doing some stuff, and they have like 4 blog posts in the blog about it. And rollups also can be seen as just execution extensions, as you can see, and that's a future I'm personally very looking forward to, that people build into one piece of software many pluggable pieces, and you run a rollup inside your own node without communication via some API. So let's build an indexer. What we want to do, we want to index the beacon chain deposits, for example, and serve them as a list of top depositors to the contract through an API. Deposits are recorded in the events of the contract, we can decode them, and the API will be the node's JSON RPC, and we extend it using our own that we will build. And this is the screenshot from the Etherscan. They already have this. So the idea is that the power is in the stack that we built, and we can use, as I said, x-axis for listening to new blocks. We decode these transactions and chain events using Alloy. For storage, I will use SQLite just because it's the safest choice for a small project. An embedded database. For the API, I will use a custom JSON RPC method, and we will bundle it all together with the node builder and test using cast from Foundry to send the RPC method, to send the RPC request to our node. So listening to new blocks. Basically the same as I showed before, same boilerplate. You have the notifications channel, you consume it, and you react on different events. Decoding the chain events. We have two definitions here. We define the deposit contract address, which is done with the address macro from Alloy, which represents the address in memory efficient way and not as a string. And here the coolest thing is the sol macro, which parses the Solidity source code and generates the Rust code from it. Basically, you'll have a struct deposit event with these fields, pub key, withdrawal credentials, etc. And it will not generate the code into a separate file, but will have it in the same file accessible through your LSP or whatever you use. And during the compilation, it will generate this code. For storage, we use SQLite. And what we store is one row per deposit. So every time we have a reorg, we have a reverted chain, and we delete all transactions that are in the reverted chain from the database. And we do it by the hash. For the commit, we do a bit more. We go through blocks in the chain, because, for example, if it's a 2D preorg block, you will have 2 blocks in the reverted and 2 blocks in the committed chain. You go through the blocks, you go through transactions with receipts, you go through the logs in each transaction, and you also filter only those transactions that are sent to the Beacon chain deposit contract. You filter the logs, you decode the logs, and then you insert this data with the amount from the log into your database. API. We define a trait that has a namespace of Devcon and the method of depositors. There is one argument, count, for limiting the output length. How many top depositors do we want to get? And this method does is querying the database with some simple SQL Web 2. We have node builder to bundle it all together. We create a new Ethereum node. We install the XX that we built. We extend the RPC with our module that we built, and we start the node. So when the node is up and running, it needs to sync. But if you already had the synced Reth node, you can use it because it's still Reth mainnet Ethereum node. You just have an extension on top of it. So if you already had a sync node, it will not have anything in the database, but it will backfill all the required blocks from Genesis. And then you will have and then you will have the depositors that you can query with cast. And cast RPC is just a command to query the JSON RPC. So the result is one file with less than 200 lines of code for building the indexer. And the power here is that you have the whole Reth code base with thousands of lines of code that's hidden by the import. And in the corner, there is a QR code. You can scan it and check out the repo. So what else can you build with X-axis? We have a couple ideas that we would like people to experiment with. And if you have any other ideas, we are very welcome, and we would love to hear it from you. So the remote XX is about streaming the data out of the node into some data lake. For example, you have a gRPC server, or you have some Kafka, or any other queue, and you just simply stream this data out and consume it on the other end. I believe this is what companies like Etherscan will do, because they will not plug the indexing part into the XX because they have a more complicated system. Oracle XX. You listen as an XX to some off-chain data source. For example, you query the New York Times web site. You attest to this data as one user of this XX. So you sign that you saw this kind of data. You gossip these attestations using the DSQ5 topic to other people running the same XX. And what you have a small network of oracles trying to agree on something, and when they come to consensus, when the quorum is reached, they post the data on chain with these signatures. So you can tell that it's actually signed by all these people who said that they're oracles. And it's very similar to how AVSs work, and you can build AVSs with X-axis. Based rollups. You expose your own RPC to send transactions. You do not post these transactions to L1, but instead you execute them on top of the state of your rollup. Then you batch them, and you submit the transactions and the state to L1. And on the QR code, we also have a bunch of examples that we built for people to play with. They're not production ready, but they serve as an inspiration for people to start working with X-axis. That's it for today. Thank you, and let's build.
Thank you very much for the wonderful talk, Alexei. So let's move to questions. As a reminder, please scan the QR code and submit your questions. So this is very dev-friendly, but you still need to run a full Reth node, right? Even just for running a simple indexer.
Yep, that's true. That's basically true. Well, yeah. You can either run an archive node to get access to all history and all change sets, or you can have a full Reth node. Yes.
Okay. How does backfill work?
Right. So when you start your XX, there is an option to subscribe to notifications telling what's the latest head that you saw is. And for example, if you start your XX on block 21 million, but you didn't start your XX on block 21 million, but you do start XX on block 21 million, but you do start your XX on block speed, I would say it's some number of gigagas mentioned per second. And this is the speed that you can get new updates at.
How do you handle reorg?
It's handled inside Reth nodes, and we basically maintain a structure, the tree that says this is the canonical chain, this is the side chain, and at some point the side chain becomes canonical. So we revert the canonical chain and make the side chain canonical. That's a rough explanation, and what you get as an XX developer is a nice diff alt new chain.
Does backfilling require running XX in archive mode, or is a full node enough?
It depends on how deep is the backfill. So in the full node, we still store some change sets. And if it's, for example, 20 blocks deep, it's fine. But if it's from Genesis, you need an archive node.
How do off-chain oracles coordinate data sources?
That's up to you. And it should be some protocol that agrees what to query, how to agree, how to communicate this data between each other, etc.
Did you see that Geth has a PR for this now too?
Yes, and unfortunately it's closed now because Peter wants to move it to his own small repo. I respect this. This is good. Yeah, I like it.
Okay. If XX runs as an independent process, what's the difference between that and other indexing tools such as the graph or other ETL tools?
You basically can choose what methods of communication it uses. And for example, you can use protobuf that's more memory efficient and space efficient.
What are invariants of the XX interface? Are notifications guaranteed to be ordered and contiguous?
Yes.
Okay. Similar to the plugin in Hyper... Oh, okay, that seems to have been Does backfill still work if you enable pruning?
Again, depends on the depth of the backfill.
Okay. Can you alter execution with XX? For example, execute some custom logic for each store.
Yes, you can. You can override it with the node builder using the custom EVM executor. It's independent from the XX, and the XX will get the result of your EVM execution.
And I think a final question. How is XX compared to Hook from Geth or plugin from Nethermind?
Right. Geth, hooks, I think require forking, and plugin from Nethermind is a cool idea that works via dynamic libraries. And I think it's very similar in terms of performance and just a different approach.
All right. Well, I think that's it for questions. Thank you very much, Alexei.
Thank you.
So we're going to have a 5-minute break before the next talk. Stay tuned. Hey guys, welcome to the session. So just as a reminder, there's going to be a QR code on display. Please scan it if you have any questions to ask. So our next speaker is Georgios from Paradigm, who will be talking about RETH 1.0, how we got to it, and what's next.
Good afternoon, everyone. It's been a wonderful day, and it was really inspiring to see so many great questions to Alexei. Just to see what's going on, by show of hands, who here is a Rust developer? Amazing. And again, by show of hands, who has contributed to any of our code bases? RETH, Foundry, Alloy, anything like that? Okay, fewer people. Who runs a node or has run a node? Okay, more people, great. Excellent, so we're going to have a high context conversation here. I'm going to talk about RETH 1.0. RETH is a new node that we started building 2 years ago. I'm going to say, how did we get here and where are we going from here? My name is Georgios. I'm the CTO and the GP at Paradigm. I'm also the founder of Ithaca, which is a project aimed at accelerating crypto. So I want to start from like, what is a node? And from a very abstract sense, a node is the soul of every network. Transactions come in, it re-executes things, it produces a state commitment, it streams the thing out, and this thing goes on. And this is what gives us the so-called decentralized cloud, decentralized web, the crypto that we all came and love. Now, today, nodes are or have been slow, they're rigid, you cannot really modify them. They're kind of scary. Like when you see somebody is running a node, you think they must be some crazy systems engineers developer. And they're actually expensive. It's really hard to run a node, as we saw a small amount of the room only running a node. And it doesn't need to be like that. Nodes must be, not can be, not should be. They must be fast so that they run the chain quickly. They must be extensible so I can go and override it and add additional functionality to it. They must be welcoming, very important. A node must not be scary. It must be a place where you go and you're not afraid to modify, to go unblock yourself. And nodes must also be cheap. They must be able to run on cheap hardware. They must require you to like get a cheap cloud box if you need, or even in your laptop. We've seen people running RETH nodes in their MacBooks, and that's really inspiring. I'm really proud of it. And so we built RETH to fix this problem. We want the nodes to be fast, so we built a fast node. And RETH is a contributor-friendly implementation of Ethereum. You can see here I have the GitHub repository. It's a repository we feel very proud of, and we're spending all of our efforts on every day. RETH was built to be fast, extensible, contributor-friendly, and cheap. And that is for many reasons. And over the last 2 years, we've been shipping and shipping and shipping. And we shipped a lot of software, and I'm excited to talk to you about a lot of this stuff today. So we started the RETH project in 2022. It was a few months into the development of Foundry, and I went to our colleague Oliver, and I'm like, okay, my man, we fixed Foundry, we fixed smart contract testing, what's next? And I told him, why don't we build a node? And he said, you're crazy. Well, a few months later, we came up with a node. We announced it in 2022, and later in 2023, we released it in the first alpha version. Doing that in 2022 was insane. I didn't know anything about nodes, but we went and studied, and we learned a lot. And today, we're seeing the benefits of learning how all of that stuff works. In 2024, RETH hit its 1.0 milestone. It was something I worked really hard on. We worked with other core dev teams, used automated client testing tools. We did everything we could to cover every single edge case. Downtime was not acceptable. Some slow transaction taking us down was not acceptable. The P2P layer taking time to sync, taking a long time to fund peers was just not acceptable. The bar is very high. And we also worked with the Sigma Prime team, our good Rust friends on the consensus layer who are also auditors. And what we did with them is we told them, okay, you guys really like the execution layer. Well, we gave you a Rust execution layer, now go crazy on it. And they found a few good things, but what was really remarkable is that the original assessment was scoped to say this long, and they ended up spending way more time because they liked the project. And that's how we want people to be working with us. We want the RETH code base to be something that people are excited to work on, and not something they find scary and like kind of like weird to be in. In 2024, RETH is being adopted in Ethereum mainnet. The data source for this is the Ethernet node crawler. Depending on what source you see, you will see different things, so bear with me. But basically, RETH is a node that appeared in 2022 and is already starting to be live and existing on Ethereum mainnet. People believe in RETH to stake their assets with it. RPC providers use REST because they find it exciting to provide better performance to their customers. And we did all of that because we want to make crypto better, and it seems that we must make crypto go faster, and that goes from all the way from the infrastructure to the developer experience. So I keep talking about contributors. This chart is kind of remarkable because this has been a chart from a few months ago, from August, and actually I tried to pull it up today, but I didn't have time to update the screenshot, but we had even more contributors and like even more PRs. We have 500 PRs and over 50 contributors every month, which is a really exciting metric to be hitting for an open source project with no grants, no subsidies, it's just cool code. And this is not a simple project, this is something complex, but somehow people keep coming to it because they like it, because there's something about like being a part of a community. And we really care about this community, about our open source developers. We have 400 contributors so far, 400 people contributing to a node. The thesis that we had when we started developing REST is not that we wanted to build a fast node to go and take over the stake or to have 33% or whatever. It was kind of an education project, honestly. It was, what if we grew the pie of open source developers that get how Ethereum works? And what if we also tapped on a group of people that care about high performance? And the result was the REST project. So to us, open source means a few things. A, there's an age-old tale from Linux, I believe, where in the eyes of 1,000 people, every bug is shallow. We get consistently bug reports for our code, and we love it. We take the bugs, we fix them, and we go to the next. And that's the nature of building such a critical project. We're very excited that we have teams like the Ethereum Foundation security team, which goes and sends us emails to our security email, and we need to fix things. And that's the beauty of open source. REST enables third-party builders. The open source community that we have built continuously builds things on REST. And REST, as Alexa said, is not just a node, it's an SDK. And it's an SDK for building high-performance nodes and so much more, like execution extensions. The other very exciting thing about the open source is that the community gives the project life. I used to be one of the main committers in the Foundry project, and nowadays the project just lives on its own. It just goes on and on and on and on, and it's kind of like remarkable, again, the beauty of open source. And finally, it has this very counterintuitive thing that if you really figure out how to solve it, the problem starts moving faster because of the third parties contributing, not slower. You don't spend all your time trying to find like great talent to come into your code base. They come to the code base because they find it cool. And we hire the best of them, like we have with the team that we have so far. Many people ask us, okay, Georgios, what you guys have done is really nice. Like, we also want to replicate this in our code base. How do we go about this? You know, do I hire a community manager? Do I hire a DevRel? What do I do? And I think there's like a lot of things that you can do. I think that most important things are on this board, and it starts with a polished issue tracker. The moment that you go to the issue tracker, you must be able to go and filter by label, good first issue, and like go pick an issue. What happens in our code bases when we open a good first issue is it gets picked up 10 minutes later. People are proud to be like putting REST on their resumes, and they're racing for open source tickets. That's really exciting. But how did we get there? We got there by having great documentation. In the Rust code bases that we have a lint that doesn't allow for any publicly exposed interface to be undocumented. The PR just fails if you don't do that. And that sounds like a small thing, but it really makes the developer think about it twice. And what I really love about the Rust programming language is that it doesn't let you be lazy, and parts of the things that we're trying to do is prevent the open source devs from being lazy when they come to our projects. Thirdly, great tests. Tests matter. We built the Foundry project again because we thought that tests matter more than people think. And here again, we think that tests matter a lot. It means that I can look at the PR like on the plane, or like when I'm like on a bicycle or anywhere, honestly, and I can know that the PR is going to be good for the PR that the marginal open source contributor brings. And that is what allows us to bring on more and more people without really having to like deal with taking hours for like PR reviews. That's really powerful. Fourth, the maintainers matter. If the maintainer is not on a chat room that like you can reach, that's a problem. If the maintainer is An asshole, that's a problem. Because if the maintainer replies to your PR and they're like, no, that PR is garbage, well, you're probably not going to go back to the repository because you think that PR was an asshole. So good vibes, they matter. It matters that when you go to the repo and you say, hey, can I take this? The person that is maintaining says, thank you for the pull request, or thank you for the issue. What about doing it this way? Instead of shutting it down, requested changes, 35 comments on the PR, and then go to the next roast. It's kind of uninspiring and demoralizing. And I think the problem with elite developers is that they think that the newbies are not worth talking to. And I think that's a cultural problem that must be fixed. And if you want an open source repository, you need that. Finally, the chat room. The chat room matters. The chat room is where the vibes happen. The chat room is where the communication happens. The chat room is where the design happens. If the chat room has non-tech spam, the chat room is not good. If there's people trolling the chat room and they make the experience uncomfortable, that's not a good chat room. God forbid there are ads in the chat room. Somebody posts a job ad or an event ad or anything like that. No bueno. It's terrible to have a bad chat room. You start ignoring it, you archive it, you don't talk about it. Our chat rooms, they have thousands and thousands of people, and somehow we managed to keep it together. And in the beginning, it required me or others on the team to go and do like manual support for a lot of people, and we were always very careful about when somebody enters the chat room, they have a good experience. The developer in an open source project as a maintainer is your customer, and you got to treat them with excellence, because for every bad developer, you lose 10. For every dissatisfied developer, you lose 10 future contributors. And that matters. Again, this is a chat about REST, but like a lot about this is about how to build successful open source projects and communities and how to ship increasingly complex projects with like small, lean, cracked teams that can do a lot of good work without having to hire 50 or 100 people and like go and burn insane amounts of money. We learned a lot. Firstly, Ethereum is just really hard. You might think that it's easy. Building a client, it was 100 times harder than I thought. Like when I told Oliver, hey Oliver, we're building a node, I thought it would have been like a 6-month project. It took 2 years. And I think building the next phase is going to take a lot longer, and that's why we're here for the long run. Big shout out to the other client teams that have been doing this for many years, and I think we're 2 years in the journey, and it's really humbling to see how hard this stuff is. Secondly, testing is extremely hard, especially when you need to interoperate with nodes in other languages, which may have different architectures. Maybe you're like built with a TriDB, maybe another DB uses the Aragon style sync. It's really interesting, like this cross-client interop. But again, it's like really what makes the problem hard and exciting to work on. And again, the best engineers want to be working on meaty, hard problems, and this is one of them. So when we see hard, we see a challenge and we go for it. Thirdly, benchmarking is extremely hard. I think benchmarking is one of the underrated things. Nobody in crypto profiles. People just like go and do cowboy modifications without thinking. The one thing that you need to do is a flame graph. A flame graph is a bar chart that you see when you run a profile or when you run a test, and it has big red boxes showing where time is spent. So I don't really know how to optimize, but I know if I see a big red box, I try to make it smaller red box. And Samply is an excellent tool that everybody that cares about performance should be using. You run Samply record your command, and it outputs a flame graph. And not only does it output a flame graph, it also outputs a Firefox share link that you can send to your teammate to continue debugging with you. It's really powerful and you need that. And fourthly, contributor friendliness is hard. I think in other languages, building successful open source projects is particularly hard because you don't really have like a bunch of like access to like easy developer tooling to make it easy to review a PR. But we did it, and we're really proud of it. All right, we got here. Where are we going? And I have 6 minutes, and I hope it's going to be enough. So 3 things for the future of REST: stability, performance, extensibility. We think of feedback loops as the most important thing. You talk to your customers, that's a feedback loop. We talk to the core devs, that's a feedback loop for our stability. If we can pass Ethereum mainnet, that's very powerful because it means that people should trust that our software is good. Similarly, what is our performance feedback loop? We built OP REST for that, which is an OP stack implementation of the REST project, and we laid out the GigaGas roadmap earlier this year on, all right, where do we need to go? Let's put a target on it, not transactions per second, gas, a real unit of account for compute, and go and like optimize that loop. And thirdly, extensibility. We have the REST SDK. OP-REST is one implementation of a node using the REST SDK. The REST SDK is a framework for building high-performance and extensible nodes, and they're stable because you know that they share code with the most important system in crypto, which is Ethereum. And execution extensions, you heard Alexei talk about, so I'm not going to talk more about it. So how did we get stability? We got it with cross-client tests and cross-client benchmarks. Big shout out the Kurtosis project and the PandaOps team for the Ethereum and the Optimism package. They let us bring up chains with as many clients that we need, as many nodes as we need, mainnet OP stack, fuzzers, any kind of third-party tooling, in 2 commands. These are wonderful tools. Anybody in node infra should be using them. Performance is, again, I'm citing the documentation on how to run REST for OP stack chains, and how to look at in our roadmap or our perspective on how to build high-performance nodes. Thirdly, extensibility. The REST SDK, we provide big examples showing a lot of things. So on the right, you will see that the execs examples for the backfill, for the execs, we have backfill, we have an oracle, we have the remote execs, we have a rollup example, we have a lot of stuff. Similarly, on the REST SDK side, we have all sorts of things. We can show you in 30 lines how to modify your EVM and add a new precompile. We can show you how to do P2P for BSC, for Polygon. Even though REST was not built for them, you can do such crazy modifications without forking the node, and you can access any chain in the ecosystem. So 2022, we started with the REST L1 node. We were able to sync something by the end of the year. By the end of 2023, we had a REST node that can sync Ethereum L1 and the OP stack. 2024 and on, REST is the SDK for building good nodes, and we're giving it away with Apache MIT license because we think the industry needs it. Our vision is to accelerate crypto alongside the open source community. That's why we started Ithaca, which is a new project that is basically taking our existing team, and we're empowered to start running experiments where we're going to start by solving the UX problem. We think that the thing that's missing right now from crypto is the UX, and really to fix the front ends, we had to fix the back ends first. Your front end is only as good as your back end, and it took 4 years, but we think that finally the stack is ready, and we're ready to finally build great experiences. And here in the right, you will see a tweet from the Ithaca account where we demonstrated what we think next generation UX can be, where we showcase EIP 7702 and P256, which are 2 proposals, one is already on L2s, and other is coming to Ethereum mainnet in a few months, where the idea there is that what if we had endgame wallet UX? What if in any device, in any chain, I can batch, no RPCs, no bridges, no gas, no key management, just works? And it's an interesting question. Can crypto UX be better than Web 2? And my claim on why people haven't been able to do that is because the pieces of the stack were not quite lined up so far. And if you see the user and the developer, anytime the user tries to do something, they go through Connect Wallet, then they go through MetaMask, then they go through Fiat onboarding, then they go through 1,000 layers, and something always quite feels off. And I think there's a time to fix it, and the time is now. And we're going to do that because we have built the industry's most used open source tools. We built Alloy, Revum, Foundry, Reth, Cryo. We just released Solar, a new Solidity compiler, Ox, WAGMI, VM. We know Ethereum, and we're going to fix it. So our North Star is to solve Ethereum's hardest problems. We've been doing it for years. We think the time is now to go and build the best open source software for the industry and for crypto to become something that we feel proud about. Thank you.
Thank you very much for the great talk, Georgios. Let's turn our attention to questions. Are there any current disadvantages of running REST compared to other clients?
Totally. There is a trade-off that you make when you're running a REST archive node, which is that you give up historical if-get proof when you run it. And right now, I believe that sometimes on the RPC, performance on the WebSocket subscription is not always state-of-the-art. So sometimes other clients can have better performance than us on the RPC, and we're working on it.
What novelty does Reth bring other than the language it's written in?
Oh, tons. Firstly, Reth, again, is an SDK, right? So the Rust language is kind of like independent here. The fact that Reth is an SDK means that I can literally go and build other node implementations using it. What it gives you is a runtime, RPC, P2P, DB, and you can choose how to put them together, and would just give you a nice builder pattern that you can use to do everything. So people have done things with Reth, for example. I think the Tycho team has done things with our stack. The Skoll team has done things with our stack. So it's not necessarily really the Rust programming language. It's that we built it to be by default performant, and like we give all the nice abstractions for people to go and build whatever the developers need, again, without forking, by being a library. So it's really critical to land this point. Reth is not just an L1 node. Like there's not much that we need to do to grow adoption on L1. We care for the stability, but like what we care about is developer tools, first and foremost, to empower devs to build things. And Reth, in every way, from the SDK standpoint, is a dev tool, and dev tools don't need to be scary.
So I can run a local ether scan with Aragon called Otterscan. When would Reth be friendly to local privacy-friendly block explorers?
That's a great question. So on Anvil, which is the testnet node that we built, which superseded Ganache, we have implemented the Otterscan API, and you can run Otterscan using Anvil. I'm not sure what happened with the. I'm not sure what happened if we have that implemented in Reth, but like maybe we could add it.
What was your thinking in starting the Reth project rather than building on Akula?
Yep.
I love Reth, but I feel bad for the Akula team.
Totally. We were looking for a very easy to contribute project, and we had a hard time like contributing to that project.
Okay. Do you have any thoughts on the Beam chain?
Not many.
Not many. Okay, then when Reth light node?
That's a great question. I don't know. Should we do one? Okay, we'll take it back to the team.
Why do you keep advertising that Reth is the most performant one when clearly Nethermind is the better one?
We love the Nethermind team, and they've been kicking our ass lately, so big shout out to the Nethermind team.
Any plans on making Consensus Client under Paradigm portfolio? Paradigm should dominate ETH ecosystem. Just relaying this, by the way, not my opinion.
Totally. These are good questions. Firstly, I see Mehdi on the crowd. We love the Lighthouse team, so no plans for anything like that. Somebody asked us around the Beam chain, should we do something about that? Oh, like it's a good opportunity. I don't know, man. I really don't know. Like we maintain so much code, it's kind of going, even consensus is hard. Like all of the stuff so far is not like the hardest, but like consensus is actually hard.
Any technical decisions on Reth that you regret?
I need to think more about it.
Okay. How do you pronounce Ithaca?
It's not Ithaca Cornell. It's Ithaca, Greece, which is an island that Odysseus from the Odyssey went back home, which is the home of Odysseus when he came back from Troy.
Okay. Is there any combination planned for Reth and Lighthouse from the perspective of EL and CL?
Oh, fuck yeah. We've been calling it Reth House, but like I don't know that it's like planned.
Okay. What specifically about Reth allows it to scale to higher gas throughput, and do you specifically measure gas in the engine?
We do use gas as our current way to measure things. We think that gas is a good enough way to address, to cover our benchmarking needs. I think it's a good question, like whether like that's a sufficient metric. For example, the gas does not express whether like well enough, like whether it's storage or compute operations. And sorry, what was the first part of the question? We lost
Reth
it.
and Lighthouse?
No.
No?
Okay, let's go on. Yeah.
All right, how'd you look at a PR on a bicycle?
Without hands, you know, like you.
Okay. When will Reth support non-op stack EVMs, and why was op stack prioritized versus other EVMs?
Yeah, so I had worked on the Optimism code base for many years, so I knew how it worked. OP stack then was designed very nicely in the sense that I can just touch the execution layer component without anything like above it, which is like the derivation function or how you do fault proofs or anything else. So it had just a nice separation where we only need to do like a few modifications to the code base, and that felt easier. And when non-OP stack chains, I don't think we have plans for us to do it, but we've been refactoring the code base to have no feature flags so that it's a pure SDK as much as possible, such that people can go and do it themselves. And we're already seeing that, for example, with the Scroll team, where the Scroll team PR'd a state commitment generalization pull request, and that state commitment generalization pull request allows them to unblock themselves and go and import Reth as an SDK and like make it work with the Merkle tree that they have, which is slightly different than the one that we have. So nothing that we will do, but like we're making the SDK available for people to do it.
All right, we're out of time for questions. Thank you again, Georgios. We'll reconvene in about 4 to 5 minutes. Hi, everyone. Welcome to the next session, current session of stage 2. So our next speaker is Guillaume, the core developer of Geth, and he will be talking about the Verkle advantage. Please welcome Guillaume, everyone.
So thanks for coming. I assume if you're here, or that's because you might have heard in the past few months some voice saying maybe Verkle is should be replaced with stacked binary trees. And the purpose of this presentation is to give you some arguments to understand why now is not the right time to do this. Let's briefly go over the current status of Verkle trees, the Verkle tree implementation in Ethereum. We launched a DevNet two weeks ago. It's chugging along fine. We have something that is pretty close to the final spec. We're missing a couple of gas costs here and there, but nothing that won't be fixed by the next DevNet. And you can go have a look at this address. It will be displayed again at the end. One of the biggest things we achieved during the last year was a Holesky shadow fork. We validated that the transition model works. So we're really proud of that, and big shout out to DevOps for helping us through this, because that was quite something. And yes, the elephant has landed. That's because the spirit animal of the stateless fork is the elephant. We simplified and clarified, so there was a big work of simplification, clarification of the gas cost EIP. So Verkle is split into 2 EIPs. One of them is 4762, the gas cost. They pertain to stateless. And then there's 6800, which is the pure description of the tree. So we had a lot of questions about it. It caused a lot of corner cases. We addressed all of that. So I'm not going to say it's completely ready, because we still need to take into account EOF 7702, and I'm sure a billion things that will come in the next 2 forks. But it's looking pretty advanced and pretty mature at this point. We also implemented the execution spec test framework. So until now, when we wanted to make sure clients agree that we don't have any consensus bugs, we used to launch a testnet and verify. But now we don't even have to do this. We just have tests that target a specific use case. So big shout out to Ignacio and of course the testing team for working on this one, because we found countless bugs before we even had to launch. So yeah, that was also a great progress this year. And then there's been experiments in implementing Verkle-friendly sync. So this one was actually done by Nethermind, by Tanishq and Nethermind, and it's the first full feature that has been implemented that hasn't first been implemented in Geth. So big shout out to Tanishq again. Right, and the last thing that we achieved last year was the state expiry. There was an EIP that was published by Han. He did a very good presentation this morning about it. So if you haven't seen it, I suggest you go and watch it. But just to give you a quick rundown, the idea is that Verkle trees are pooling their leaves together by groups of 256. And then they have some kind of extension stem on top of it, and the commitment, which commits to the orange box, which is the commitment. What we do is we add a new field that used to be 0, and now it's the epoch number, so it's backwards compatible. It's really good. And when you want to delete some data, you just delete the whole 266 values, and you just keep the commitment. And because everything is polynomial based, you can provide a proof of the entire subtree. So you have to resurrect the whole subtree in one go, but it's great because effectively you only keep the internal nodes, and the internal nodes is where Verkle trees especially shine. This is what takes the less space in the whole thing. So it will provide a state expiry scheme that is efficient, that is pretty much turnkey. We could activate on it on day one of Verkle, and yes, it's very simple in the sense you don't need address space extension, you don't need to do any modification. It's really working out of the box. So the conclusion is that after 4 years, Verkle is pretty much ready for its prime. Of course, I'm not going to pretend it's ready to ship tomorrow. We still have a couple things to do, but I think within a year we'll be you know, a year of focused work. Of course, we could be ready to ship. Let's go over the pros and cons of Verkle for the rest of this discussion. The first pro is that if you take the Verkle proof and the Verkle witness, this is really small, and this is like much smaller than any alternative you can think of. We had several experiments, and we found some encoding that is especially efficient, so it's known as type 3 here. The average size is like 400 kilobytes, less than 400 kilobytes, and the worst case that we observed, so we replayed historical blocks. Caveat, of course, they did not, because they're historical block, they didn't have the whole Verkle gas cost activated, but it's still a very interesting reference. What we see is that the worst case is less than 1 megabyte. The theoretical worst case is 3 megabytes, but on average it's less than 400 kilobytes, which is really good because you've probably have heard about increasing the gas limit, increasing the blob count. All of this is going to have an impact on the bandwidth. So the fact we have a very efficient proof structure, something that like we will add some size, but adding very little compared to any other option is definitely a plus. The trees itself is small. It's like on average from measurements we've made, so we take an MPT, we convert it to Verkle, and we see what the end result is. It's about 25% smaller. We have optimizations where we could shave yet another maybe 10, 20 gigabytes still. But more importantly, it's also changing the way we store the data, so you can write to the DB more efficiently, at least the guest DB. This is my reference. So this is something that's very useful. One of the really good things about Verkle, or at least stateless, actually, it's not even just Verkle, but you can immediately join the network when you want to sync. And then you can download the data you're missing. If you want to build a full node, you can download the data you're missing in the background. But unlike the current experience where you just wait for the blocks to be downloaded and then the state, and then you hope that you've got everything in order to be able to follow the chain. You start following the chain right off the bat, and only then do you worry about downloading the data. So if you want to compare the idea of a Verkle sync to the current state of SnapSync, what happens in SnapSync is that you start downloading the state here, I'm using sprouts because I want to point out that the data at this stage is fresh. It's the latest data you've got. But as blocks keep being added to the chain, the node keeps downloading data, but the old data, like the data that was downloaded before, is actually becoming stale. So this is represented by dried leaves. So what you have to do is go to the network and ask nodes that are synced to send you the data that is obsolete.